Earth was once very different from what it is today. The continents and oceans we know now did not exist. Instead, large ancient oceans covered much of the planet and changed over time as the Earth's surface shifted. More than 4 billion years ago, the young Earth began to cool after its formation. Thick clouds filled the atmosphere, and rain fell for long periods, collecting in low areas to form the first oceans. These early oceans were not stable. The Earth's crust was still moving and breaking apart, causing oceans to form, expand, shrink, and disappear. Over millions of years, different oceans appeared and vanished as the continents slowly moved. These prehistoric oceans helped shape the surface of the Earth, influenced the climate, and created the conditions that allowed life to begin. The Panthalassic Ocean was an enormous and all-encompassing ocean that once dominated the surface of the Earth. Its name comes from ancient Greek words that mean all and sea, and this name perfectly reflects its true nature. It was not just a large ocean like those we know today, but a single, continuous body of water that stretched across nearly the entire planet. At a time when the world looked completely different, this vast ocean surrounded a giant landmass known as Pangaea, which brought together almost all of Earth's continents into one enormous block of land. Around 250 million years ago, during a major transition in Earth's history between the Paleozoic and Mesozoic eras, Panthalassa covered close to 70% of the planet's surface. The remaining land, forming roughly one-third of the surface, was gathered into Pangaea. This arrangement created a world with one giant ocean and one giant continent, a configuration very different from the scattered continents and multiple oceans we see today. The scale of Panthallassa was far greater than any modern ocean, even larger than the present-day Pacific Ocean, which is considered its direct descendant. Over time, the original floor of this massive ocean did not survive. The outer edges of continents acted like slow-moving conveyor belts, pulling the oceanic crust downward into the Earth's interior in a process known as subduction. Because this process continued for millions of years, almost all traces of Panthalassa's original seafloor were destroyed. What scientists know today comes from fragments left behind along continental edges and from advanced techniques that allow them to look deep into the Earth's interior and detect the remains of ancient oceanic plates that have sunk into the mantle. The story of Panthallassa is deeply connected to even older geological events. Long before Pangaea existed, another supercontinent called Rodinia dominated the planet. Around 870 million to 845 million years ago, Rodinia began to break apart. This breakup was likely caused by powerful forces deep within the Earth, where rising heat and material from the mantle created stress in the crust. These internal movements weakened the supercontinent and caused it to fracture. Around 750 million years ago, the process continued as the western portion of Rodinia began to split further. Large sections of land that would later form parts of Africa, Asia, and other regions drifted away from what is now known as Laurentia, an ancient core of North America. By about 720 million years ago, additional land masses, including areas that would become Australia and East Antarctica, had separated. These movements gradually reshaped the planet, creating new ocean basins and eventually leading to the formation of Panthallassa. As time passed and continents shifted, the structure of Panthallassa became more complex. During the early Jurassic period, a major reorganization of tectonic plates took place beneath the ocean. A new oceanic plate system began to form, where three large plates met in what is known as a triple junction. These plates, called the Farallon, Phoenix, and Izanagi plates, were part of the vast Panthalassic Ocean floor. Their movements marked the early stages of the modern Pacific system, showing how the ancient ocean gradually transformed into the oceans we recognize today. Because most of Panthalassa's ocean floor has been lost, scientists rely on indirect evidence to reconstruct its history. Along the edges of continents, they find pieces of crust and rock formations that did not originally belong there. These fragments, known as terranes, were once located far out in the ocean and were carried across great distances by moving tectonic plates. Over time, they collided with continents and became attached to them. These terranes often contain volcanic rocks and marine fossils, providing valuable clues about the environment and conditions of the ancient ocean. In regions such as northeastern Asia, Japan, and western North America, these terrains preserve evidence of volcanic island chains that once existed in Panthalassa. These island arcs formed above subduction zones, where one tectonic plate was forced beneath another. As the plates moved, these arcs were transported and eventually merged with continental land masses. Modern scientific methods, such as seismic imaging, allow researchers to study the Earth's interior and identify the remains of subducted plates. These remnants help scientists map out the locations of ancient subduction zones and better understand the structure of Panthallassa. The boundary between Panthallassa and another ancient ocean, known as the Tethys Ocean, remains difficult to fully reconstruct. This is because the oceanic crust that once separated them has almost entirely disappeared. Both the Panthallassic and early Pacific seafloors have been subducted, leaving very little direct evidence behind. Today, the region where these oceans once interacted is part of Southeast Asia, an area characterized by a complex network of tectonic plate boundaries and ongoing geological activity. During the Permian period, which took place before the rise of dinosaurs, Panthallassa hosted numerous underwater mountains known as seamounts. Near the equator, these seamounts supported the growth of coral reefs and atolls, forming small, ring-shaped islands. As tectonic processes continued, many of these seamounts were carried toward continental margins and eventually became attached to them. These ancient reef structures can still be observed today as limestone formations in places like Japan, where they provide a glimpse into the ocean's distant past. Life within Panthallassa was both diverse and remarkable. Among the most notable organisms were fusilians, a group of single-celled marine creatures. Despite their simple structure, some fusilians grew to surprisingly large sizes, reaching up to 16 centimeters in length. They developed complex internal features and often lived in partnership with photosynthetic algae, which provided them with energy. This period of rapid growth and diversification occurred during the late Carboniferous and early Permian periods and is known as a major biodiversity expansion. However, this flourishing of life did not last forever. Around 260 million years ago, a significant extinction event disrupted marine ecosystems and greatly reduced the diversity of fusilians. Only smaller and less complex forms survived this event. Later, around 252 million years ago, a much larger and more devastating extinction occurred, known as the Permian-Triassic extinction event. This event marked the end of the Permian period and resulted in the extinction of a vast number of species, including the remaining fusilians. The immense size of Panthallassa had a profound impact on how life evolved within it. Because the ocean was so vast, populations of organisms could become isolated from one another for extremely long periods. This isolation allowed different groups to evolve independently, adapting to unique environmental conditions. For example, if chains of underwater volcanoes moved at a rate of only a few centimeters per year, it could take up to 100 million years for different groups of organisms to come into contact again. As a result, distinct regions of the ocean developed their own unique ecosystems. Changes in climate also played an important role in shaping the history of Panthallassa. Toward the end of the Permian period, global temperatures dropped, leading to the formation of large ice sheets on land. This caused sea levels to fall significantly, altering marine habitats and contributing to widespread extinctions. Although scientists continue to study the exact causes of these events, it is clear that changes in climate and sea level had a major impact on life in the ocean. Panthallassa was not only vast in size, but also dynamic in its behavior. Its currents and circulation patterns were influenced by global wind systems and temperature differences. Despite its enormous scale, the ocean did not remain still or uniform. Instead, it developed complex patterns of movement, including large rotating systems known as gyres. These gyres existed in both the northern and southern parts of the ocean and played a key role in distributing heat and nutrients. In the northern part of Panthallassa, strong winds created large circular currents that moved water across vast distances. Trade winds near the equator pushed water westward, while winds at higher latitudes caused it to flow in different directions. As water accumulated along the western edges of the ocean, it was redirected, forming powerful boundary currents. These currents helped create a continuous cycle of movement, ensuring that water circulated throughout the ocean. A similar system existed in the southern part of Panthallassa, although the direction of rotation was opposite. Currents near the equator flowed westward, while those closer to the poles moved in different patterns. Together, these currents formed a large, interconnected system that influenced the distribution of heat and the movement of marine life. Temperature differences across the ocean also played a significant role in its behavior. In some regions, cooler water rose from the depths to the surface, bringing nutrients that supported marine ecosystems. In other areas, warmer water spread across the surface, creating different environmental conditions. These variations helped shape the distribution of life within the ocean and influenced global climate patterns. Panthalassa also played an important role in the geological development of continents. Along its margins, tectonic activity led to the formation of mountain ranges and the growth of continental edges. For example, the western edge of ancient North America, known as Laurentia, developed through the gradual addition of terranes and volcanic arcs that were carried by oceanic plates. This process, known as accretion, continued over millions of years and contributed to the formation of major geological features. In regions like Eastern Australia, similar processes occurred as oceanic material was added to the continent. These additions formed complex geological structures, including volcanic arcs and sedimentary basins. Over time, these features recorded the history of subduction and plate movement along the margins of Panthalassa. Even today, remnants of these ancient processes can be found in the rocks of Australia and nearby regions. As the Earth continued to evolve, Panthalassic gradually gave way to new ocean systems. The breakup of Pangaea led to the formation of smaller oceans and the separation of continents. New ocean basins opened, and the global arrangement of land and water began to resemble the modern world. Despite this transformation, the influence of Panthalassa did not disappear. Its legacy can still be seen in the structure of today's oceans, particularly in the Pacific, which carries forward many of its characteristics. The Tethys Ocean was a vast and important ocean that existed long before the world we know today took shape. It stretched across the planet during much of the Mesozoic era and continued into the early to middle part of the Cenozoic era. This ancient ocean played a crucial role in shaping modern geography because it eventually gave rise to familiar bodies of water such as the Indian Ocean, the Mediterranean Sea, and inland seas like the Black Sea and the Caspian Sea. In the early days of the Mesozoic, the Earth's land was joined together in one massive supercontinent known as Pangaea. As this enormous landmass slowly began to split apart, the Tethys Ocean formed in the wide space between two huge sections, Gondwana in the south and Laurasia in the north. Over time, as the continents continued to drift, the meaning of the Tethys Ocean changed. Later, especially during the Cretaceous period, it referred to the ocean bordered by the continents that would become Africa, Eurasia, India, and Australasia. As the Earth entered the early to middle part of the Cenozoic era, massive movements of the planet's crust began to reshape the ocean dramatically. Huge pieces of the Earth's surface, such as the Indian, African, Australian, and Arabian plates, slowly moved northward and collided with the Eurasian plate. These collisions were not gentle. They pushed up enormous mountain ranges in a long belt known as the Alpide Belt, which includes famous ranges like the Alps, Himalayas, Zagros Mountains, and Caucasus Mountains. These rising mountains acted like barriers, cutting off the natural flow of ocean currents between what would later become the Indian Ocean and the Mediterranean region. At the same time, global sea levels dropped due to the formation of ice in Antarctica. Together, these changes gradually destroyed the Tethys Ocean as a single, continuous body of water, breaking it apart into smaller seas and oceans. Long before the Tethys Ocean existed, there had been an earlier ocean called the Paleotethys Ocean, which lasted from the time of the Cambrian period until the early part of the Triassic period. Later, a newer version called the Neotethys Ocean formed during the late Triassic and continued in some form until around 24 million to 21 million years ago, when it finally closed completely. Part of this ocean became isolated and formed a large inland sea known as the Prototethys Sea. This sea lasted for a long time, but eventually shrank and mostly dried up around 5 million years ago. Today, the Black Sea and the Caspian Sea are considered the last surviving pieces of that ancient inland sea. The name Tethys comes from Tethys, a figure from Greek mythology who was believed to be a powerful water goddess. She was said to be the sister and partner of Oceanus, and the mother of countless river gods, sea nymphs, and freshwater sources. Geologists sometimes divide the Tethys Ocean into eastern and western parts. The western side, often called the Tethys Sea or Western Tethys, was not a single open stretch of water. Instead, it was a complex region filled with smaller ocean basins, islands, and fragments of continents. These pieces were separated by shifting plates and shallow seas that covered large areas of land during times when global sea levels were high. Many of these shallow seas spread across parts of what is now Europe, creating environments rich in marine life. During the early part of the Cenozoic era, the Tethys Ocean could be thought of as three main regions. One was the Mediterranean Tethys, which later became the Mediterranean Sea. Another was the Peritethys, a vast inland sea that once covered large areas of Eastern Europe and Central Asia and eventually evolved into the Prototethys Sea. The third was the Indian Tethys, which later became the Indian Ocean. A waterway known as the Turgai Strait once connected the Tethys Ocean to the Arctic Ocean, allowing water to flow between these distant regions. As scientific understanding improved over time, researchers began using the name Tethys more broadly to describe a whole series of ancient oceans that existed at different times. These include the Paleotethys, the Mesotethys, and the Neotethys, each representing a stage in the long and complicated history of ocean formation and continental movement. These oceans should not be confused with the Rheic Ocean, which existed to the west during an earlier period. To the north of the Tethys lay a landmass called Angara Land, while to the south stretched Gondwana Land. Even earlier, between about 600 million and 360 million years ago, there was another ocean called the Prototethys Ocean. It lay between the northern land masses of Baltica and Laurentia and the southern supercontinent Gondwana. Over hundreds of millions of years, pieces of land slowly broke away from Gondwana and drifted northward, eventually forming much of Asia. Around 250 million years ago, during the Triassic period, a new ocean began to form as a crack opened along the northern edge of southern Pangaea. A piece of land known as Cimmeria slowly drifted northward over tens of millions of years, pushing the older ocean floor beneath it and creating the Neotethys Ocean in its place. By about 150 million years ago, during the Jurassic period, this drifting landmass finally collided with Laurasia. This collision caused the ocean floor behind it to bend downward, forming a deep trench, while rising sea levels flooded large parts of Europe with shallow waters. At the same time, Laurasia and Gondwana continued to move apart, opening up new ocean space that would eventually become part of the Atlantic Ocean. Because North and South America were still attached to these larger landmasses, the Tethys Ocean once formed part of a continuous band of water that stretched around the Earth near the equator. Ocean currents during this time flowed very differently from those of today, creating unique global climate patterns. Between the Jurassic and the later part of the Cretaceous period, beginning around 100 million years ago, Gondwana broke apart further. Africa and India drifted northward across the Tethys, while the Indian Ocean began to open. During this time, the Tethys Sea was full of life. Its waters were home to a wide variety of marine creatures, including reptiles, fish, and soft-bodied animals like cephalopods. The islands scattered across the northern parts of the Tethys, especially in what is now Europe, created isolated environments where animals evolved in unusual ways. Some dinosaurs became smaller over generations, a process known as insular dwarfism, as seen in creatures like Telmatosaurus. At the same time, some flying reptiles became much larger, a process called insular gigantism. One of the most impressive examples was Hatzegopteryx, a massive predator that likely ruled the skies and hunted like a top predator. Toward the end of the Cretaceous, especially during the Maastrichtian, the Tethys Sea was also home to many giant marine reptiles known as mosasaurs. In regions like Europe and North Africa, several large species lived at the same time, competing with each other for food and dominance. This intense competition between top predators was similar to what happened in other ancient seas, such as the Western Interior Seaway of North America. During the long stretch of Earth's history known as the Cenozoic, which began about 66 million years ago and continued until the early part of the Neogene around 23 million years ago, the great connections between the Atlantic Ocean and the Indian Ocean slowly began to disappear. These connections had once flowed through the ancient Tethys Ocean, a vast body of water that had existed for millions of years. Over time, powerful forces deep within the earth reshaped the surface. The land masses of Africa and Arabia steadily drifted northward, inch by inch, pressing into Eurasia. At the same time, global sea levels were dropping, partly because enormous amounts of water were becoming locked away in ice as the Antarctic ice sheet formed and expanded in the far south. This gradual closing of the ocean pathways did not happen all at once. Instead, it unfolded in two major stages. The first took place around 20 million years ago, and the second followed roughly 6 million years later, around 14 million years ago. As these connections narrowed and finally shut, the Tethys Ocean was effectively cut off, and this had far-reaching consequences for the entire planet. Ocean currents, which had once flowed freely across vast distances, were forced to reorganize themselves. This shift helped create strong upward movements of deep, nutrient-rich water in the Arabian Sea, a process known as upwelling. These changes also played an important role in shaping the powerful seasonal wind system now known as the South Asian monsoon. In addition, major global ocean systems such as the Atlantic meridional overturning circulation and the Antarctic circumpolar current were significantly altered, changing how heat and water moved around the Earth. Earlier, during the Oligocene, which lasted from about 33.9 million to 23 million years ago, large parts of Central and Eastern Europe were not land as we see them today. Instead, they were covered by a northern extension of the Tethys Ocean, known as the Prototethys. This body of water was separated from the main Tethys as massive mountain chains began to rise during a period of intense geological activity called the Alpine orogeny. These mountains included the Alps, the Carpathian Mountains, the Dinaric Alps, the Taurus Mountains, and the Elburz Mountains. As these structures pushed upward, they cut off the Prototethys from the larger ocean. By the later part of the Miocene, the Prototethys had begun to shrink. What had once been a wide and connected sea slowly turned into a series of isolated inland waters. In its earlier phase, when it first became separated during the early Miocene, life in the Prototethys actually flourished. There was an increase in primary productivity, meaning that microscopic organisms like algae grew in large numbers, forming the base of the food chain. However, this period of growth did not last. As time went on, rapid chemical changes, especially the breakdown of carbonate materials, caused the entire ecosystem to collapse. Many species could no longer survive in the changing conditions, and the once thriving environment declined dramatically. In the year 1845, the British geologist Roderick Murchison carefully described a unique geological formation that stretched from the Black Sea to the Aral Sea. He noticed that the fossils found there were different from those of earlier, fully marine environments. In regions such as Crimea and Taman, just south of the Sea of Azov, the rock layers matched those found around the modern Caspian Sea. These rocks contained shells from freshwater organisms mixed with species that could live in slightly salty or brackish water. This unusual combination of life forms revealed that the waters in these regions were neither fully fresh nor fully marine, but something in between. Similar fossil patterns were discovered across vast areas of the southern and southeastern plains, showing how widespread this environment once was. Murchison also created a map showing what he called the Aralo-Caspian Formation. This stretched from near the delta of the Danube River across Crimea, up along the eastern side of the Volga River to the region of Samara, and then south of the Ural Mountains to areas beyond the Aral Sea. Today, scientists know that layers from the Miocene period, containing both brackish and freshwater deposits, extend through regions such as the North Alpine Foreland Basin and into the Swabian Jura. In some places, these deposits reach thicknesses of up to 250 meters, showing just how extensive these ancient environments were. At the time these layers formed, the front edge of the Alps was located about 100 kilometers farther south than it is today. In the year 1885, the Austrian paleontologist Melchior Neumayer studied marine sediments from the Mesozoic and noticed a pattern in their distribution across different regions. From this, he concluded that a vast ocean must once have existed. He called this idea the Central Mediterranean Sea and described it as a seaway during the Jurassic period, stretching all the way from the Caribbean region to the Himalayas. A few years later, in the year 1893, the Austrian geologist Eduard Suess developed this idea further. He proposed that a great inland sea had once existed between the northern supercontinent Laurasia and the southern landmasses that later formed Gondwana. He named this ancient sea after Tethys from Greek mythology. To support his theory, he carefully studied fossil evidence found in both the Alps and parts of Africa. He later presented his ideas in a major work titled Das Antlitz der Erde, which means the face of the earth. In the early decades of the 20th century, several geologists who believed that continents could move, known as mobilists, expanded on this idea. Scientists such as Franz Uhlig, Karl Diener, and Johannes Dacqué described the Tethys as a vast trough lying between two giant land masses. According to them, this ocean existed from the later part of the Paleozoic until pieces of Gondwana drifted northward and eventually closed it. After the end of World War II, scientists began to picture the Tethys as a triangular ocean, wide in the east and narrowing toward the west. However, not all geologists agreed. Between the 1920s and the 1960s, another group known as fixists believed that the continents did not move. They saw the Tethys not as a single ocean, but as a complex system that changed shape through repeated cycles of mountain building. They used different names, Paleotethys, Mesotethys, and Neotethys, to describe these stages, linking them to major geological events such as the Caledonian orogeny, the Variscan orogeny, and again the Alpine orogeny. Later, during the 1970s and 1980s, scientists also introduced the term Prototethys, though these names were sometimes used in different ways by different researchers. Despite these differences, the central idea remained the same. A vast ocean once existed, pushing into the supercontinent Pangaea from the east, much as Suess had originally suggested. In the 1960s, a major breakthrough came with the widespread acceptance of the theory of plate tectonics. This theory finally explained how the Tethys Ocean had disappeared. It showed that the Earth's crust is made of moving plates, and that oceanic crust can sink beneath continental crust in a process called subduction. With this understanding, scientists could clearly see that the Tethys was not just a shallow sea, but a true ocean that had been slowly destroyed as its floor was pushed down beneath surrounding continents. By the early 1970s, several researchers, including A.G. Smith and teams led by James Dewey, John Pittman, William Ryan, Jean Bonnin, Henri Laubscher, Daniel Bernoulli, Bernard Bijou-Duval, Jean Dercourt, and Xavier Le Pichon, came to regard the Tethys as an oceanic plate in its own right. This marked a major step forward in understanding the true nature of this long-vanished ocean and the powerful forces that shaped its history. The Iapetus Ocean was one of the ancient oceans that existed hundreds of millions of years ago, during a time when the Earth looked very different from how it does today. This ocean first appeared in the late Neoproterozoic era and continued to exist into the early Paleozoic era, roughly between 600 million years ago and 400 million years ago. It occupied a position in the southern hemisphere, lying between vast landmasses that geologists today refer to as Laurentia, Baltica, and Avalonia. These continents were separate from each other, forming islands and stretches of continental crust scattered across the ancient oceans, and the Iapetus Ocean filled the space between them like a watery highway that connected and separated these landmasses at the same time. Over time, the Iapetus Ocean ceased to exist as a distinct body of water because the continents surrounding it began to drift toward each other. This drift was driven by the movement of the Earth's tectonic plates, large sections of the Earth's crust that slowly shift over geological time. As Laurentia, Baltica, and Avalonia approached each other, the ocean that once lay between them gradually narrowed and eventually disappeared. Its closure occurred through a series of dramatic geological events known as orogenies, or mountain-building episodes. Specifically, the Tectonic, Caledonian, and Akkadian orogenies played critical roles in this process. These events involved the collision and welding together of the continents, ultimately forming a single large landmass known to geologists as Euramerica. The southern portion of the Iapetus Ocean is thought to have closed in a similar but slightly more distant scenario. Here, the closure occurred when the western edge of the massive Gondwana continent, located in the southern hemisphere and including much of what is today South America, collided with Laurentia. This collision is reflected in geological formations seen today in both North and South America, suggesting that the tectonic orogeny of the North was a continuation of a chain of mountain-building activity visible in Argentina, called the Famattinian orogeny. Together, these events stitched together previously separate continents into larger, more continuous landmasses. Interestingly, the Iapetus Ocean can be seen as a sort of ancient precursor to the modern Atlantic Ocean. Much like the Atlantic, the Iapetus opened along zones where the Earth's crust was pulling apart, and its expansion and later closure show parallels with the processes that later created the Atlantic Ocean during the Jurassic period, nearly 150 million years ago. In recognition of this connection, the ocean was named after Iapetus, a titan in Greek mythology who was the father of Atlas, the figure whose name would later be given to the Atlantic Ocean. This naming reflects both a symbolic and scientific link between the two oceans, highlighting how Earth's history repeats in cycles over immense spans of time. The story of the Iapetus Ocean began to emerge more clearly in the early 20th century, when American paleontologist Charles Walcott made important observations. Walcott studied trilobites, a type of extinct marine arthropod that thrived in shallow seas, which lived on the continental shelves of Laurentia and Baltica. He noticed significant differences in these trilobite communities. For example, Laurentia was home to a group called the Olanellidae, sometimes referred to as the Pacific fauna, and their fossils were found in areas that are now part of western Newfoundland and Scotland. In contrast, Baltica contained a distinct group called the Paradoxididae, known as the Atlantic fauna, which appeared in the southern regions of the British Isles and eastern Newfoundland. These differences suggested that the two continental regions had been separated by a significant marine barrier during the early Paleozoic, a separation that Walcott and his contemporaries described as a geosyncline, or a large trough-like depression in the Earth's crust. This geosyncline, they believed, had kept the faunas of Scotland and England apart, creating distinct marine environments. Later developments in geology, particularly the establishment of plate tectonic theory in the 1960s, transformed our understanding of these ancient oceans. Geologists such as Arthur Holmes and John Tuzo Wilson recognized that the Atlantic Ocean could not have formed in isolation. It must have had a predecessor, and the Iapetus Ocean fit this role. Wilson, in particular, noted that the Atlantic had opened along roughly the same zone where the Iapetus had once closed, leading him to formulate the Wilson cycle. This cycle describes the repeated opening and closing of oceans over hundreds of millions of years, as continents drift apart and then collide again, producing mountain ranges and new ocean basins in the process. The Iapetus Ocean, therefore, represents a fundamental example of the cyclical nature of Earth's tectonic activity. Geological evidence of the Iapetus Ocean's formation is found in several parts of the world. In Scandinavia, for instance, basaltic dikes have been dated to between 670 million and 650 million years ago. These dikes are fractures in the Earth's crust through which molten rock once flowed, and they indicate that rifting, or the pulling apart of the continental crust, had begun by that time. This rifting would eventually create the basin that became the Iapetus Ocean. Similarly, in Newfoundland and Labrador, geologists have studied the long-range dikes, which formed during the same rifting events, providing further evidence that the Iapetus Ocean was taking shape. Additional geological formations, such as the Fen complex in Norway and the Alno complex in Sweden, are interpreted as the result of mild extension in the ancient continent of Baltica that accompanied the opening of the Iapetus Ocean. The timing of the ocean's formation, however, varied across different regions. The eastern Iapetus Ocean, located between Laurentia and Baltica, is thought to have begun opening around 590 million years ago, coinciding with the emplacement of the central Iapetus magmatic province. This was a large volcanic and magmatic event that marked the initial separation of the two continents. Meanwhile, the southern portion of the ocean, situated between Laurentia and southwestern Gondwana, began to open approximately 550 million years ago, near the end of the Ediacaran period. This period immediately preceded the Cambrian, a time known for the explosive diversification of life. At the same time that the southern Iapetus was opening, another ocean farther east, called the Adamastor Ocean, was closing. These overlapping events illustrate the dynamic and complex nature of Earth's oceans during this period. It is worth noting that the opening of the Iapetus Ocean appears to post-date the opening of another ancient ocean, the Puncoviscana Ocean, which likely formed around 700 million years ago as Laurentia began drifting away from Amazonia. The Iapetus Ocean and the Puncoviscana Ocean were separated by a long, narrow strip of continental crust known as the Arequipa Antofalla terrane, yet their formation seems to have occurred independently. This shows that multiple oceanic basins could form simultaneously in different parts of the globe, each influenced by local tectonic conditions rather than being directly connected. Along the western edge of the Iapetus Ocean, the early Cambrian, beginning about 540 million years ago, witnessed the development of a volcanic island arc. This arc emerged above a subduction zone, a region where one section of the oceanic crust slid beneath another. As the oceanic lithosphere of the Iapetus Ocean subducted southward, magma was generated and rose to form islands, creating a chain of volcanoes that marked the leading edge of tectonic convergence. This process also caused the western portion of the Iapetus Ocean to gradually shrink as oceanic crust was consumed by subduction. Farther north and east, similar processes took place. Avalonia and Baltica began moving toward Laurentia during the Ordovician period, roughly 488 to 444 million years ago. These convergences further narrowed the ocean and set the stage for its eventual closure. Evidence from the fossil record confirms these changes. Trilobites living on the continental shelves of Baltica and Laurentia remained distinct during the Ordovician, reflecting the continued separation of the continents by oceanic waters. However, as the continents drew closer, especially during the Silurian period, approximately 444 to 420 million years ago, trilobite faunas began to mix. This progressive blending of species reflects the gradual closing of the ocean and the establishment of new ecological connections between previously isolated marine habitats. The closure of the Iapetus Ocean occurred in stages. In the west, the Tectonic orogeny, which took place between 480 and 430 million years ago, marked a significant collision event. During this orogeny, the volcanic island arc formed above the subduction zone collided with Laurentia, effectively consuming the western branch of the ocean. Some geologists also consider the oceanic basin south of the island arc to be part of the Iapetus, which closed later during the Akkadian orogeny when Avalonia collided with Laurentia. Meanwhile, the southern Iapetus Ocean, as previously mentioned, closed when Laurentia collided with western Gondwana. This collision produced mountain ranges and deformed rocks that remain visible today in regions such as Argentina and parts of North America, providing a record of the immense forces involved. In the eastern regions, the closure occurred as well. The Tornquist Sea, a branch of the Iapetus, disappeared during the late Ordovician when Avalonia and Baltica collided. The main branch of the ocean, separating Baltica, Avalonia, and Laurentia, closed during the Grampian and Scandian phases of the Caledonian orogeny, which occurred between 440 and 420 million years ago. By this time, tectonic forces had finally brought the continents together, leaving no significant open ocean between them. By the end of the Silurian period, approximately 420 million years ago, the Iapetus Ocean had completely vanished. Its disappearance marked the creation of a new continental landmass composed of the once separate continents of Laurentia, Baltica, and Avalonia. This newly assembled continent, called Laurasia, would later form the northern part of the supercontinent Pangaea, a vast landmass that encompassed nearly all of the Earth's continents during the late Paleozoic and early Mesozoic eras. The history of the Iapetus Ocean, therefore, represents a critical chapter in the story of continental assembly, ocean formation, and the tectonic cycles that have shaped the surface of the Earth over hundreds of millions of years. The geological processes that created, expanded, and eventually closed the Iapetus Ocean are a vivid illustration of the Earth's dynamic nature. Rifting, subduction, island arc formation, and continental collision all played essential roles in the life cycle of this ancient ocean. Its formation was marked by the stretching and thinning of continental crust, volcanic activity, and the creation of new oceanic lithosphere. Its closure was characterized by the consumption of oceanic crust at subduction zones, the collision of volcanic arcs with continents, and the ultimate welding together of separate land masses into a single continental mass. Fossil evidence, particularly from trilobites, provides a unique window into these ancient processes. The distinct species found on Laurentia, Baltica, and Avalonia tell a story of isolation and gradual reconnection. As the continents drifted and collided, these marine organisms recorded the changing geography, giving modern scientists a biological measure of tectonic movements. Trilobite faunas from the Ordovician and Silurian periods, for instance, reveal the gradual merging of previously isolated ecosystems, reflecting the progressive narrowing of the Iapetus Ocean. Geologists also rely on the study of rock formations to reconstruct the ocean's history. Basaltic dikes, volcanic complexes, and magmatic provinces mark the sites of rifting and ocean opening, while orogenic belts and deformed rock sequences reveal the sites of collisions and ocean closure. The central Iapetus magmatic province, the Fen complex, the Alno complex, and the long-range dikes are all examples of geological features that serve as evidence for the ocean's opening and evolution. Similarly, the Tectonic, Akkadian, and Caledonian orogenies leave behind mountain ranges, metamorphic rocks, and fault systems that record the dramatic collisions that closed the ocean and created new continental crust. The Iapetus Ocean story is also closely tied to the concept of supercontinents and oceanic cycles. The opening and closing of this ocean demonstrate how the Earth's surface undergoes continuous transformation, with oceans forming and disappearing as continents drift across the globe. The Iapetus Ocean opened as continents separated, expanded as rifting progressed, and eventually closed as tectonic forces drove continents together. Its existence provides a clear example of the Wilson cycle, the repeated pattern of ocean formation and closure that shapes the Earth's continents over geological time. Moreover, the Iapetus Ocean shows the interconnectedness of global tectonic events. Its opening coincided with the closure of other oceans, such as the Adamastor, while its formation post-dated earlier oceans like the Puncoviscana. This highlights the fact that Earth's tectonic history is not a linear sequence of events, but rather a complex, overlapping series of processes that interact across the planet. Each ocean, each continental drift, and each collision is part of a larger dynamic system, demonstrating the interconnectedness of geological phenomena over hundreds of millions of years. The Iapetus Ocean was a vast body of water that existed during a very distant chapter of Earth's history, stretching from the late Neoproterozoic into the early Paleozoic, roughly between 600 million and 400 million years ago. At that time, the continents were not arranged the way they are today. Instead, several ancient land masses, known as paleocontinents, were scattered across the globe. This ocean lay mainly in the southern hemisphere and formed a wide, watery barrier between three of these major land masses, Laurentia, Baltica, and Avalonia. Over an immense span of time, the Iapetus Ocean did not remain unchanged. It slowly shrank and eventually disappeared as the continents on either side of it moved closer together. These movements were not sudden or violent in a human sense, but incredibly slow, happening over tens of millions of years as Earth's crust shifted and rearranged itself. The closing of this ocean was marked by a series of powerful mountain-building events known as orogenies, including the Tectonic orogeny, the Caledonian orogeny, and the Akkadian orogeny. During these events, the once separated continents collided and fused together, forming a much larger landmass called Euramerica. There is also an idea that a southern part of the Iapetus Ocean closed in a similar way, through collisions involving the western edge of Gondwana and Laurentia. This process may have been linked to the Famattinian orogeny as well as the Tectonic orogeny, suggesting that different parts of the ocean were closing at different times, but through related tectonic processes. Because of where it was located, the Iapetus Ocean is often seen as an early version, or a kind of ancestor, of the Atlantic Ocean. Long after the Iapetus had vanished, the continents that once bordered it would drift apart again, eventually forming the coastlines of the modern Atlantic. In fact, the way the Iapetus Ocean first opened shows strong similarities to how the Atlantic Ocean began to form much later during the Jurassic period. Its name reflects this connection. It was named after Iapetus, a figure in Greek mythology who was said to be the father of Atlas, the namesake of the Atlantic Ocean. In the early years of the 20th century, scientists began to notice clues that hinted at the existence of this lost ocean. One important figure was Charles Walcott, who studied ancient marine fossils called trilobites. These small, hard-shelled creatures lived on the seafloor and left behind fossils that are still found today. Walcott observed that trilobites from Laurentia were very different from those found in Baltica. For example, species belonging to the Olenalidae, often called the Pacific fauna, were found in places like Scotland and western Newfoundland, while species from the Paradoxididae, known as the Atlantic fauna, appeared in the southern British Isles and eastern Newfoundland. These differences suggested that the regions had once been separated by a large ocean, preventing the mixing of species. At that time, geologists did not yet fully understand plate tectonics, so they proposed the idea of a deep trough, or geosyncline, lying between areas such as Scotland and England. This hypothetical feature was thought to explain why the fossils were so different on either side. Everything changed in the 1960s, when the theory of plate tectonics became widely accepted. Scientists like Arthur Holmes and John Tuzo Wilson realized that oceans can open and close over time as continents move. Wilson, in particular, noticed that the Atlantic Ocean seemed to have formed in roughly the same place where an older ocean had once existed. This insight led him to propose what is now called the Wilson cycle, a concept describing how oceans are born, grow, shrink, and eventually disappear. Physical evidence for the opening of the Iapetus Ocean can still be found today in ancient rocks. In parts of Scandinavia, for example, there are long, dark sheets of volcanic rock known as basaltic dikes that formed between about 670 million and 650 million years ago. These rocks are believed to have formed when the Earth's crust began to stretch and crack, a process known as rifting, which eventually led to the creation of the ocean basin. Similar features, such as the long-range dikes in Newfoundland and Labrador, also point to this period of early stretching and separation. Other geological formations, like the Fen complex in Norway and the Alnö complex in Sweden, may have formed as a result of mild tectonic stretching in the ancient continent of Baltica after the ocean began to open. These features act like fingerprints, preserving the story of how the land once pulled apart. The opening of the Iapetus Ocean did not happen all at once, but in stages. The eastern part likely began forming around 590 million years ago, when large amounts of molten rock rose up and created what is known as the Central Iapetus Magmatic Province between Laurentia and Baltica. The southern part opened slightly later, around 550 million years ago, as Laurentia drifted away from what is now South America, then part of Gondwana. Around the same time, another ocean to the east, called the Adamastor Ocean, was closing. Even earlier, another ocean known as the Punkoviscana Ocean may have opened around 700 million years ago, when Laurentia separated from the Amazonian region. The Iapetus Ocean was separated from this earlier ocean by a long, narrow strip of land called the Arequipa Antofalla terrane. Although these oceans formed at different times, scientists believe their origins were not directly connected. As time went on, the Iapetus Ocean began to shrink. To the southwest, a chain of volcanic islands started forming from the early Cambrian period, around 540 million years ago. This island arc developed above a subduction zone, where one part of the ocean floor was being forced beneath another. This process slowly consumed the oceanic crust, making the ocean narrower. From about 550 million years ago onward, the western part of the ocean continued to shrink as subduction progressed. Meanwhile, in the north and east, the continents of Avalonia and Baltica began moving steadily toward Laurentia, starting in the Ordovician period, which lasted from about 488 million to 444 million years ago. Fossils provide a fascinating record of these changes. During the Ordovician, trilobite species in Baltica and Laurentia were still quite different, showing that the ocean was still wide enough to keep them apart. However, by the Silurian period, these differences began to fade as species from both sides started to mix. This gradual blending of life forms reflected the closing distance between the continents. Eventually, the ocean disappeared entirely. In the west, it closed during the Tectonic orogeny between about 480 million and 430 million years ago, when a volcanic island arc collided with Laurentia. Some scientists believe that a southern branch of the ocean also closed later during the Akkadian orogeny, when Avalonia finally collided with Laurentia. At the same time, the eastern parts of the ocean were also closing. A smaller body of water known as the Tornquist Sea between Avalonia and Baltica vanished during the late Ordovician. the main eastern branch of the Iapetus Ocean, closed later during different phases of the Caledonian orogeny, including the Grampian phase and the Scandian phase, between about 440 million and 420 million years ago. By the end of the Silurian period, around 420 million years ago, the Iapetus Ocean had completely vanished. In its place stood a newly formed continent called Laurasia, created from the merging of Laurentia, Baltica, and Avalonia. This landmass would later become the northern half of the supercontinent Pangaea, one of the most famous and important stages in Earth's geological history. The Rheic Ocean was one of the most significant oceans in the Paleozoic era, acting as a vast body of water that separated two enormous land masses, known as paleocontinents, which are ancient continents that existed hundreds of millions of years ago. These two continental giants were Gondwana, an immense landmass that occupied much of the southern part of the Earth, and Laurasia, a combination of smaller landmasses, including Laurentia, Baltica, and Avalonia. In the grand history of our planet, the Rheic Ocean played a pivotal role in shaping the geography, climate, and life forms of its time. The remnants of this ocean, in the form of sutures or zones where its waters once lay, stretch across the modern world for more than 10,000 kilometers, beginning in what is now Mexico and continuing all the way across Europe to modern-day Turkey. The eventual closing of the Rheic Ocean, through the massive movement of tectonic plates, was not merely a geographic event. It was a dramatic collision of continents that led to the creation of one of Earth's most famous supercontinents, Pangaea. This colossal assembly was accompanied by the formation of massive mountain ranges geologists today refer to as the Veruscan, Alleghanian, and Ouachita orogenies, which are the results of intense compressional forces as continents collided and crumpled against one another. To understand the Rheic Ocean fully, we must first trace its origins and predecessors. Long before the Rheic came into being, the world had already been home to an earlier ocean named the Iapetus, which existed during the early Cambrian period. The name Iapetus was drawn from Greek mythology, honoring the Titan Iapetus, who was said to be the father of Atlas, the giant who held up the heavens. This link is more than mythological. The name Atlantic Ocean, which dominates our modern Earth, ultimately traces its origins back to Atlas and the mythological Iapetus, showing the deep continuity between ancient and modern oceans. Just as the Iapetus Ocean separated landmasses before the Rheic, it served as a precursor to the Atlantic, dividing early continents and setting the stage for subsequent oceanic formations. As the early Ordovician period began, a new ocean started to emerge between Gondwana and Laurasia, and this ocean was named the Rheic, drawing inspiration from Greek mythology once again, this time after Rhea, the sister of Iapetus. By adopting the name of a titaness, geologists recognized the ocean's importance as a major player in Earth's geological and biological history. At the very start of the Paleozoic era, roughly 540 million years ago, most of the Earth's continental mass was concentrated around the South Pole. The dominant landmass of the time was Gondwana, a giant continent encompassing regions that today would include Africa, South America, Australia, Antarctica, and the Indian subcontinent. While Gondwana was enormous and largely southern, the northern regions of the planet were dotted with smaller continental fragments, among which Laurentia and Baltica were particularly significant. The Paleozoic oceans, including the Iapetus, lay between these land masses, forming the dynamic aquatic zones that facilitated the movement of land fragments and the evolution of life. Along the northern edge of Gondwana, a period of intense geological activity had already taken place during the Ediacaran period, just before the Cambrian explosion. This activity, known as the Cadomian orogeny, involved the formation of a cordillera-like chain of volcanic mountains, where sections of oceanic crust were subducted beneath Gondwana. In simpler terms, the oceanic crust of the Paleozoic oceans sank beneath the continental crust of Gondwana, creating high mountain ranges and volcanic arcs, just as the Andes Mountains rise above subduction zones in the modern world. As time progressed, around the late Cambrian into the early Ordovician period, this dynamic geological environment led to the creation of extensional basins along the northern margin of Gondwana. These basins were regions where the crust was being pulled apart, forming depressions that would eventually evolve into rift zones. This rifting along the northern edge of Gondwana was crucial, because it eventually led to the birth of the Rheic Ocean. The rift itself gradually expanded and developed into a mid-oceanic ridge, a type of underwater mountain chain formed by upwelling magma, similar to the mid-Atlantic ridge we see today. This process effectively separated smaller continental fragments, including Avalonia and Carolina, from the main body of Gondwana. In this way, the Rheic Ocean began to take shape in the early Ordovician, as water flooded the newly created rift, separating these land fragments from Gondwana and creating a significant new oceanic expanse. As Avalonia and Carolina drifted northward, moving away from Gondwana, the Rheic Ocean expanded further, reaching its maximum width of approximately 4,000 kilometers during the Silurian period. This process of ocean widening and continental drifting coincided with the gradual closure of the Iapetus Ocean, as Avalonia and Carolina collided with Laurentia, resulting in the dramatic Appalachian orogeny, a massive mountain-building event in what is now eastern North America. The Rheic Ocean did not remain open indefinitely. Its eventual closure began in the early Devonian period, and by the Mississippian period, Gondwana and Laurentia had fully collided, bringing the Rheic Ocean to an end. This closure was not merely a simple disappearance of oceanic waters, it represented one of the most significant collisional events in Earth's history. The immense pressure and tectonic forces generated by the convergence of these continental giants produced the largest collisional mountain systems of the Paleozoic era. These included the Variscan and Alleghanian orogenies, which stretched from the western margin of Gondwana, in the area corresponding to modern-day West Africa, across southern Baltica, and into eastern Laurentia. Simultaneously, the Ouachita orogeny formed where the Amazonian margin of Gondwana collided with southern Laurentia, creating yet another extensive belt of folded and uplifted mountains. These mountain systems were not only geological landmarks, they profoundly influenced ocean currents, climate patterns, and habitats for early life, shaping the course of evolution during the late Paleozoic. Amid the vast waters of the Rheic Ocean, numerous smaller features also played crucial roles in the planet's ecological and evolutionary history. One remarkable example is the Prague Basin, a region that during the Silurian period consisted of a series of humid volcanic islands situated on the outer edges of the Gondwanan Shelf. These islands were geologically dynamic, rising and eroding quickly due to volcanic activity. They formed an archipelago, a group of islands in the Rheic Ocean, which became a hotspot of early plant life during the initial phases of the Silurian-Devonian terrestrial revolution. The rapid formation and destruction of these islands created diverse microenvironments, with each island potentially hosting unique plant communities. This high rate of ecological turnover, combined with the isolation of island ecosystems, likely encouraged high levels of endemism, meaning many species evolved uniquely in these islands and were not found elsewhere. These processes are believed to have been instrumental in the rapid early diversification of vascular plants, which were beginning to colonize the land and transform Earth's landscapes during this period. The closure of the Rheic Ocean and the massive geological changes it triggered had far-reaching consequences for life on Earth, particularly in marine ecosystems. As Gondwana collided with Laurentia and Laurussia, the planet underwent dramatic environmental transformations. In addition, this tectonic activity coincided with the onset of the late Paleozoic Ice Age, a period of extensive glaciation that further influenced ecosystems both on land and in the oceans. These combined geological and climatic pressures created conditions that are thought to have driven one of the most significant evolutionary events of the Paleozoic era, the Carboniferous earliest Permian biodiversification event. During this event, marine life experienced a remarkable increase in species richness, with particularly notable expansions among fusellinids, a group of single-celled organisms with complex shells, and brachiopods, marine animals with hard shells resembling clams. This diversification added complexity to marine ecosystems, with new species filling various ecological niches and contributing to the intricate web of life that characterized late Paleozoic oceans. The early Paleozoic, therefore, must be seen as a period of extraordinary transformation, with the Rheic Ocean acting as both an agent and a witness to the shifting continents, rising mountains, and emerging life forms. Its creation involved the careful orchestration of tectonic events that separated Avalonia and Carolina from Gondwana, forming a mid-oceanic ridge and expanding the oceanic expanse over millions of years. Its growth facilitated the closure of older oceans, like the Iapetus, and enabled the collision of continental fragments that gave rise to some of the earliest major mountain ranges in Earth's history. The process of closure, meanwhile, compressed and folded vast regions of continental crust, leading to the Variscan, Alleghanian, and Ouachita mountain belts that remain evident in the geological record. These orogenies not only shaped the surface of the planet, but also influenced climate and biogeography, guiding the distribution of plants, animals, and marine life across different regions. Even the small features within the Rheic Ocean, such as the Prague Basin, highlight the intricate relationship between geology and biology. The volcanic islands of this basin, constantly reshaped by eruptions and erosion, offered unique habitats for early vascular plants, which were experimenting with life on land. The high rate of environmental change, combined with isolation on islands, likely accelerated evolution, allowing new species to emerge and diversify in a relatively short geological time. In this way, the Rheic Ocean was not just a physical space between continents, but a laboratory of evolution, where geological dynamics and biological innovation were tightly intertwined. The timing of the ocean's closure also had profound implications. Occurring during the early Devonian to Mississippian periods, the collision of Gondwana with Laurussia coincided with broader global changes, including glaciations and shifts in sea level, which affected both terrestrial and marine ecosystems. The Carboniferous earliest Permian biodiversification event exemplifies the scale of ecological transformation linked to these tectonic processes. Marine species, particularly fusulinids and brachiopods, proliferated, increasing the complexity and richness of ocean ecosystems and demonstrating how geological events directly influenced evolutionary pathways. Thus, the Rheic Ocean's life cycle, from formation, expansion, and peak width to eventual closure, represents a critical chapter in Earth's history, illustrating the profound interconnections between tectonics, oceanography, and the evolution of life. The Paleotethys Ocean, sometimes written as Paleotethys, was one of the ancient oceans that played a critical role in the ever-changing configuration of Earth's landmasses and oceans. It existed along the northern edge of the supercontinent Gondwana, a massive landmass that contained what we now know as Africa, South America, Antarctica, India, and Australia. The ocean began to form during the Middle Cambrian period, which occurred roughly around 510 million years ago. Over the vast expanse of geologic time, the Paleotethys grew, shifted, and eventually disappeared during the late Triassic period, around 220 million years ago. This means that the Paleotethys Ocean existed for approximately 400 million years, making it one of the longest-lived oceans in Earth's history. The Paleotethys is especially interesting because it served as a precursor to the later Tethys Ocean, which is sometimes referred to as the Neotethys. The Neotethys formed between Gondwana and a collection of land fragments known as the Rheic Terranes, which had broken off from Gondwana and drifted northward. To understand this, it is important to know that in the process of continental drift, entire land masses and fragments of continental crust can split away from a supercontinent and slowly move across the planet's surface. In the case of the Paleotethys, its opening occurred as an even older ocean called the Prototethys Ocean subducted or slid beneath these drifting terranes. Eventually, the Paleotethys itself closed as new land masses called the Cimmerian terranes broke away from Gondwana and moved northward. These shifts in continental positions helped pave the way for the emergence of the Neotethys Ocean. The terminology surrounding these ancient oceans can be a little confusing. For instance, the Neotethys is sometimes defined as the ocean that existed south of a hypothesized mid-ocean ridge, a type of underwater mountain chain which separated Greater India from the rest of Asia. In that case, the ocean situated between the Cimmerian terranes and this hypothetical ridge is referred to as the Mesotethys or Middle Tethys. The naming of these oceans often depends on the perspective and definitions chosen by geologists, and such distinctions can be subtle but important when reconstructing the paleogeography of Earth hundreds of millions of years ago. The Rheic terranes themselves were divided into two main groups. The European Rheic terranes correspond to regions of present-day Europe, specifically areas like Armorica and the Iberian Peninsula, while the Asiatic Rheic terranes refer to parts of the crust beneath southern Asia. Between these two groups of terranes ran a large transform fault, which is a type of fault where sections of the Earth's crust slide past one another horizontally. This fault acted as a boundary that separated these drifting continental fragments and played an important role in the movement and shaping of the Paleotethys Ocean. The role of the Paleotethys Ocean in the broader cycles of supercontinents, especially in the breakup of the massive supercontinent Pangaea, is still a subject of debate among geologists. Some scientists argue that the opening of the North Atlantic Ocean, which began to form between the Americas and Eurasia, was triggered by the subduction of the Panthalassic Ocean, the enormous global ocean that surrounded Pangaea beneath the western margins of the Americas. In this scenario, mantle plumes, which are columns of hot, upwelling rock from deep within the Earth, caused the Atlantic Ocean to open and contributed to the fragmentation of Pangaea. The closure of the Paleotethys and the later Tethys Oceans would then be seen as consequences of these larger tectonic processes. In another view, geologists propose that the forces which closed the Paleotethys and Tethys Oceans were transmitted along a roughly east-west axis, affecting regions that today form the Mediterranean. In this model, these longitudinal forces eventually contributed to the initial opening of the Atlantic Ocean. Both perspectives highlight the complex interplay between oceanic subduction, continental drift, and mantle dynamics in shaping Earth's surface. The formation of the Paleotethys Ocean can be traced back to events in the late Ordovician period, approximately 450 million years ago. At that time, back-arc spreading, a process in which the Earth's crust stretches and pulls apart behind a subduction zone, caused the European Hunnic terranes to separate from Gondwana. These terranes began moving northward toward another ancient landmass known as Euramerica, which is also called the Old Red Sandstone Continent. This movement was accompanied by the subduction of the oceanic plate located beneath the Rheic Ocean, an older ocean that lay between Euramerica and the European Hunnic terranes. Rifting in this subducted plate created a small ocean known as the Hercynian Ocean, which persisted until the late Carboniferous period, roughly around 300 million years ago. During the early Devonian period, approximately 420 million years ago, the eastern part of the Paleotethys Ocean began to open more widely. This was a result of the northward movement of the Asiatic Hunnic terranes, which included microcontinents such as the North and South China blocks. These movements caused significant changes in the size and shape of surrounding oceans. As the Asiatic terranes moved north, the Prototethys Ocean gradually shrank, eventually disappearing by the late Carboniferous period when the Chinese blocks collided with the Siberian continent. At the same time, in the early Carboniferous, roughly around 355 million years ago, a new subduction zone developed to the south of the European Hunnic terranes. This zone began to consume the oceanic crust of the Paleotethys Ocean, marking the beginning of its gradual closure. Gondwana itself also began drifting northward, which contributed to the closure of the western portions of the Paleotethys Ocean. By the Carboniferous period, continental collisions occurred between the Old Red Sandstone Continent and the European Hunnic terranes. In North America, this collision is known as the Alleghenian orogeny, while in Europe it is called the Variscan orogeny. During these events, the Rheic Ocean completely disappeared, and the western Paleotethys Ocean was steadily closing. By the late Permian period, around 260 million years ago, the small, elongated Cimmerian plate broke away from Gondwana. This plate represents what today forms the crust of modern-day Turkey, Iran, Tibet, and parts of Southeast Asia. As it separated, a new ocean, the Tethys Ocean, began forming to its south. Meanwhile, the Paleotethys Ocean continued to shrink, and by the late Triassic period, only a narrow seaway remained. In the early Jurassic epoch, roughly around 190 million years ago, as part of the Alpine orogeny, the remaining oceanic crust of the Paleotethys subducted beneath the Cimmerian plate, completing the closure of the ocean from west to east. Some geologists suggest that a last remnant of the Paleotethys Ocean may persist today as part of the oceanic crust beneath the Black Sea. In this region, Anatolia, which lies south of the Black Sea, represents part of the original Cimmerian continent that once formed the southern boundary of the Paleotethys. Geographically, the Paleotethys Ocean occupied a location that today corresponds roughly to the Indian Ocean and parts of southern Asia. During its existence, the equator ran along the length of the ocean, giving it a tropical climate. This tropical setting likely supported lush coastal and island environments, which were home to dense forests. These forests, over time, contributed to the accumulation of coal deposits, which can still be found in certain regions today. The Paleotethys Ocean not only illustrates the complex history of ocean formation and closure, but also reflects the dynamic processes that have continually reshaped Earth over hundreds of millions of years. Its interactions with surrounding continents, terrains, and other ancient oceans demonstrate the interconnected nature of tectonic processes, subduction, rifting, and continental drift. These processes have had long-lasting impacts on global geography, climate, and the distribution of natural resources such as coal. From its birth during the Middle Cambrian through its expansion and eventual closure in the late Triassic, the Paleotethys Ocean played a crucial role in the story of Earth's geological past. Its legacy is visible today in the arrangement of continents, the presence of certain mountain ranges formed during continental collisions, and in remnants of its oceanic crust preserved beneath modern seas such as the Black Sea. The Mesotethys Ocean was a significant but often overlooked chapter in the long and intricate history of Earth's oceans, a transitional water body that existed during the ever-changing landscape of our planet's surface. It acted as a bridge, both in terms of geography and geologic time, between the older Paleotethys Ocean and the later Neotethys Ocean, reflecting millions of years of tectonic shifts, continental drift, and dramatic changes in Earth's configuration. To understand the Mesotethys, one must first appreciate the story of the oceans and continents around it, as this ocean was not an isolated feature, but part of a dynamic and constantly evolving system. The Paleotethys Ocean, which preceded the Mesotethys, was located along the northern edge of the vast southern supercontinent known as Gondwana. Gondwana itself was composed of what are now Africa, South America, Antarctica, Australia, the Indian subcontinent, and the Arabian Peninsula. The Paleotethys opened during the Middle Cambrian, roughly 510 million years ago, and grew throughout the Paleozoic era, only to eventually close in the late Triassic, around 225 million years ago. Its existence, stretching over approximately 400 million years, left a lasting imprint on the regions it touched, influencing the formation of mountains, basins, and sedimentary deposits. As this ocean began to shrink, due to the northward movement of terrains and microcontinents that collided with Gondwana, a complex geological transition was initiated. This is where the Mesotethys emerges as a distinct entity in the oceanic record. The Mesotethys Ocean appeared during a period of major reorganization of Earth's land masses, roughly in the late Carboniferous to early Permian, around 320 to 290 million years ago. It occupied a space that was once part of the Paleotethys, but as the older ocean closed, new seaways and rift zones opened. These rifts were created as parts of Gondwana's northern margins started to break apart and drift. The Mesotethys was neither as vast as the global oceans of its time, nor as confined as the basins that would eventually become the Neotethys, but it represented an important transitional oceanic corridor that connected and separated major landmasses. In many ways, it was a laboratory for tectonics, where subduction zones, rift valleys, volcanic arcs, and microcontinents interacted in a highly dynamic environment over tens of millions of years. During the existence of the Mesotethys, the northern margin of Gondwana was particularly active. Large chunks of continental crust, often referred to as terrains, were moving northward. These terrains included pieces of what would later become parts of southern Europe, Iran, Turkey, and Southeast Asia. As these terrains drifted over the Mesotethys Ocean, they gradually collided with the remnants of the older oceanic crust, and with each other, forming mountain ranges and complex suture zones. Some of these collisions left behind chains of volcanic islands and underwater mountain ridges, which in turn influenced ocean currents and sedimentation patterns. This process of terrain movement and collision was a precursor to the much larger and more famous closure of the Neotethys Ocean in the Mesozoic and Cenozoic eras, which eventually contributed to the rise of the Himalayas and other major mountain ranges. The ocean itself was relatively narrow compared to the vast Panthalassic superocean, which covered much of the Earth's surface at the time. Estimates suggest that at its maximum extent, the Mesotethys stretched several thousand kilometers from east to west, though its exact dimensions changed continually as tectonic plates moved. The ocean was likely deep in the central regions, hosting abyssal plains and deep basins where sediments gradually accumulated. These sediments, composed of clay, silt, and carbonate materials, were later uplifted during collisions and now form important geological formations across southern Europe, the Middle East, and Asia. Near the continental margins, the ocean was shallower, with continental shelves hosting reefs and shallow marine ecosystems. Fossils found in these regions indicate the presence of diverse marine life, including trilobites, brachiopods, ammonoids, early mollusks, and primitive fish species. These fossils help geologists reconstruct the paleogeography of the time and understand the complex interplay between tectonics and life. The Mesotethys was also marked by active volcanic arcs, formed as the oceanic crust subducted beneath the moving terrains and microcontinents. Subduction zones generated significant volcanic activity, both underwater and on emerging islands, creating chains of volcanoes that contributed volcanic ash and lava to the ocean floor. These volcanic materials mixed with the sediments carried by rivers from the surrounding landmasses, resulting in complex stratigraphy that preserves a record of both tectonic and biological evolution. Some of these volcanic arcs later accreted to the continents during collisions, forming part of the complex geological mosaics seen in regions like the Alps, the Zagros Mountains, and the Hindu Kush. The ocean was not static. It underwent periods of widening and narrowing due to the shifting of tectonic plates. In the early Permian, roughly 290 million years ago, the Mesotethys was likely at its most extensive, stretching between the moving northern terrains and the stable southern edge of Gondwana. As the Permian progressed into the Triassic, around 250 million years ago, the ocean began to shrink as rifting continued and new microcontinents moved northward. By the late Triassic, approximately 225 million years ago, much of the Mesotethys had been consumed by subduction, and the Neotethys Ocean began to emerge as the dominant seaway in the region. This transition was gradual, involving the rearrangement of oceanic crust, the formation of new ocean basins, and the accretion of terrains to form the continental fragments that we now recognize as parts of Europe, Asia, and the Middle East. The closing of the Mesotethys Ocean was accompanied by significant geological activity. As terrains collided with Gondwana, large-scale deformation occurred, resulting in thrust faulting, folding, and metamorphism of rocks along the suture zones. These processes created mountain ranges and highlands that influenced global climate, ocean currents, and sediment transport. Rivers flowing from these uplifted regions carried sediments into adjacent basins, gradually filling them and leaving behind sequences of sedimentary rocks that are still studied today. These sedimentary sequences preserve a record of changing sea levels, climate variations, and biological evolution, providing a window into Earth's deep past. Biologically, the Mesotethys Ocean served as a conduit for species migration and diversification. Its waters connected the northern and southern hemispheres in certain regions, allowing marine species to disperse across vast distances. At the same time, the dynamic tectonic environment created isolated basins and marginal seas where species could evolve independently. This combination of connectivity and isolation contributed to the diversification of marine life during the late Paleozoic and early Mesozoic. Fossil evidence from carbonate platforms, reef systems, and deep marine sediments indicates the presence of a wide variety of invertebrates, early corals, bryozoans, and mollusks, as well as early fish species that were beginning to diversify into more modern forms. The Mesotethys Ocean, therefore, played a key role in shaping the evolutionary pathways that would later influence life in the Neotethys and beyond. The sediments of the Mesotethys also record environmental changes, including fluctuations in sea level, climate shifts, and episodes of anoxia, where oxygen levels in the deep waters dropped significantly. Such anoxic events are preserved in black shale deposits, which are rich in organic matter and later became important sources of hydrocarbons. These deposits demonstrate that the Mesotethys Ocean was not only a site of tectonic activity, but also a dynamic chemical and biological system, responding to changes in global climate and the movements of continents. The combination of tectonics, sedimentation, and biological evolution made the Mesotethys a particularly complex and fascinating oceanic system. The Mesotethys also had a profound influence on the distribution of land and sea during the formation of the supercontinent Pangaea. As the Mesotethys narrowed and eventually closed, it facilitated the amalgamation of northern Gondwana with the terranes and microcontinents drifting from the north. This contributed to the final assembly of Pangaea by the late Permian, roughly 255 million years ago, when almost all of Earth's major landmasses were connected into a single supercontinent. The closure of the Mesotethys thus represents a key step in the long process of continental assembly that reshaped the planet's oceans, climates, and ecosystems. Although the Mesotethys Ocean existed during a transitional period and lasted for tens of millions of years, its impact was long-lasting. It set the stage for the Neotethys Ocean, which opened in the Triassic around 225 million years ago and persisted into the Cenozoic. The Neotethys was larger and more significant in terms of global ocean circulation and continental separation, but it inherited much of its configuration from the earlier Mesotethys, including rift zones, volcanic arcs, and sedimentary basins. Without the transitional stage provided by the Mesotethys, the evolution of the Neotethys and the tectonic history of the region would have been very different. In modern times, geologists study remnants of the Mesotethys through a combination of fieldwork, fossil analysis, and geophysical methods. Suture zones, ophiolite complexes, and metamorphic belts provide clues to the location and evolution of the ocean. Fossils preserved in the sedimentary rocks along the former margins of the ocean help reconstruct its environmental conditions and marine biodiversity. Geochemists analyze isotopic compositions in the rocks to understand the timing of ocean opening and closure, as well as the rates of sedimentation and tectonic uplift. These studies contribute not only to our understanding of ancient oceans, but also to broader questions about the movement of continents, the evolution of marine ecosystems, and the history of life on Earth. The Neotethys Ocean, an immense body of water that existed during the Mesozoic era, which spanned roughly from 250 million to 66 million years ago, was one of the most important oceans in Earth's long and intricate geological history. This ocean was located in a position that now corresponds to the region between the ancient supercontinents of Laurasia to the north and Gondwana to the south. To fully understand the significance of the Neotethys, it is necessary to consider the broader context of how continents, oceans, and the surface of the Earth evolved over hundreds of millions of years, and how the movements of massive landmasses, known as tectonic plates, continually reshaped the planet's geography, climate, and even life itself. The story of the Neotethys begins with the breakup of the enormous supercontinent Pangaea, which dominated the Earth's surface during the early Mesozoic. Pangaea was a colossal landmass that brought together almost all of the planet's continental crust into one contiguous expanse. As the Earth's tectonic plates shifted, this single supercontinent began to fragment. To the south, the massive landmass known as Gondwana began to drift northward, carrying with it smaller continental blocks, including microcontinents like Cimmeria, which were fragments of continental crust that rifted away from Gondwana's northern edge. To the north, Laurasia remained relatively stable, but began to act as a barrier, preventing the southern continents from freely merging with the northern landmasses. It was between these two great continental regions that the Neotethys Ocean began to open, forming a vast expanse of water stretching eastward, a process that would continue and intensify over tens of millions of years. The opening of the Neotethys was closely linked to the rifting and drifting of the Cimmerian microblocks. These small continental fragments separated from Gondwana in a slow but steady journey northward, effectively enlarging the oceanic gap between the two great supercontinents. This motion was facilitated by the dynamic activity of the Earth's lithosphere, where the crust and the upper mantle are broken into plates that move over the more fluid asthenosphere below. As these microblocks moved, they left behind an ever-widening oceanic corridor, allowing seawater to flood into areas that were previously shallow seas or even dry land. Over millions of years, this process transformed the region into a true ocean, with deep basins, shallow continental shelves, and complex coastlines that would influence ocean currents, climate patterns, and the habitats available for marine life. The Neotethys Ocean played a critical role not only in shaping the geography of the Mesozoic Earth, but also in influencing biological evolution. As an expansive marine corridor, it connected distant regions and allowed for the migration of marine species across long distances. This ocean provided a wide range of environments, from warm, shallow waters along continental margins to deeper basins in the central parts of the ocean. Coral reefs, ammonites, and other marine organisms thrived in these environments, leaving behind fossil evidence that helps modern scientists reconstruct the ocean's history. Furthermore, the Neotethys was a stage for the first significant diversification of many marine groups during the Mesozoic, an era sometimes called the Age of Reptiles, not only because of the reptiles dominating the land, but also because of the extraordinary variety of life in the seas. As the Cimmerian blocks continued their journey north, the Neotethys Ocean gradually narrowed in certain regions. The most dramatic consequence of this northward drift was the eventual collision between the Neotethys and the southern edge of Eurasia. This collision did not happen all at once, but took place over tens of millions of years, as the oceanic lithosphere of the Neotethys was slowly subducted beneath the Eurasian plate. Subduction is a process where one tectonic plate sinks beneath another into the mantle, and it generates enormous forces that deform the Earth's crust. These forces were responsible for the creation of one of the most famous mountain chains in the world, the Alps-Zagros-Himalayan orogenic belt. This belt stretches from Europe through the Middle East and into southern Asia, marking the locations where the collision between the Cimmerian microblocks, the remnants of Gondwana, and Eurasia caused the crust to crumple, fold, and uplift into towering mountains. The Alps, located in Central Europe, were formed from the western portion of this collision system. Millions of years of tectonic stress, erosion, and sediment deposition created the dramatic landscapes that are recognizable today, with peaks exceeding 4,000 meters. Farther east, in the region now occupied by Iran and Iraq, the Zagros Mountains arose in a similar process, sculpted by the immense pressures of converging plates. Finally, the collision of India, which had broken away from Gondwana, with Eurasia gave rise to the Himalayas, the tallest mountains on Earth, with peaks rising above 8,000 meters. This monumental event, which continues to have geological consequences even today, was a direct outcome of the Neotethys Ocean's closure and the northward movement of Gondwana-derived landmasses. The Neotethys Ocean also had a profound effect on the climate of the Mesozoic world. Oceans play a crucial role in regulating global climate by distributing heat through currents and by storing and cycling carbon. The presence of such a large ocean between the continents meant that monsoon-like systems could develop, influencing rainfall patterns over vast regions of the adjacent continents. The eastward orientation of the ocean created pathways for oceanic currents that carried warm water from the equator toward higher latitudes, moderating temperatures and influencing marine ecosystems. In addition, the slow closure of the ocean and the uplift of mountain ranges altered wind patterns, precipitation, and the distribution of deserts and forests, setting the stage for the complex climate systems that would dominate the later Cenozoic era. Geologically, the Neotethys was not a simple, uniform ocean, but a complex and dynamic system. Its seafloor consisted of both old and newly formed oceanic crust, created by the process of seafloor spreading at mid-ocean ridges. This created a variety of structures, including basins, ridges, and fracture zones. Volcanic activity was common along subduction zones, where oceanic lithosphere was consumed beneath continental margins. These volcanoes produced vast deposits of ash and lava, some of which are now preserved as sedimentary rocks or volcanic layers in mountain belts. Moreover, the sediments carried by rivers from nearby continents accumulated on the ocean floor, forming thick sequences of sandstones, shales, and limestones that record the gradual history of the ocean and its interactions with land masses. The Neotethys Ocean was not static. It experienced cycles of expansion and contraction throughout the Mesozoic. During periods when the Cimmerian blocks moved rapidly, new oceanic basins opened, extending the reach of the ocean and providing fresh habitats for marine life. During periods when these blocks slowed or collided with Eurasia, the ocean narrowed, and large-scale subduction consumed the seafloor, pushing continents closer together. These dynamic changes were recorded in the geological record as sequences of marine deposits interspersed with evidence of tectonic uplift, erosion, and mountain building. By studying these rocks, modern geologists can reconstruct the timing and processes of the Neotethys evolution, tracing the steps that led to the modern configuration of continents and oceans. Another remarkable aspect of the Neotethys was its influence on the development of mineral resources. As sediments accumulated in the ocean basins, they trapped organic material, which over millions of years transformed into fossil fuels such as oil and natural gas. The subduction and collision processes created zones of intense heat and pressure, leading to the formation of valuable mineral deposits, including metallic ores like copper, lead, and zinc. These resources, which are crucial for human industry today, owe their origins to the long history of the Neotethys and its complex interplay between oceanic and continental processes. In addition to its geological and climatic impacts, the Neotethys Ocean played a significant role in the eventual formation of the Indian Ocean and the Mediterranean Sea. As the ocean gradually closed in its western regions, remnants of its waters were trapped between colliding landmasses, forming the Proto-Mediterranean basins. In the east, the northward drift of India and its collision with Eurasia contributed to the isolation of the Indian Ocean as a separate body of water, which would later take on its modern form. In this way, the Neotethys can be considered a precursor to these modern oceans, and understanding its history helps explain the distribution and connectivity of present-day marine environments. The closure of the Neotethys was not a rapid event. It was a drawn-out process that unfolded over tens of millions of years. The initial collisions created shallow seas and marginal basins, while later stages involved the consumption of vast stretches of oceanic crust through subduction. Some parts of the Neotethys were consumed entirely, leaving no trace of the original ocean, while other areas survived as narrow seas or elongated basins that would eventually merge into the modern Mediterranean. The subduction zones also generated deep ocean trenches, volcanic arcs, and mountain ranges, which further complicated the geography of the region and contributed to its rich geological diversity. The history of the Neotethys Ocean also illustrates the concept of plate tectonics in action. It provides a vivid example of how oceans and continents are not fixed but constantly move, interact, and transform over geological time. The northward drift of Gondwana, the separation of microblocks like Samaria, and the eventual collision with Eurasia are all processes that demonstrate the power of Earth's internal forces. These movements are driven by convection currents in the mantle, which slowly push and pull the overlying plates. Over millions of years, these forces have reshaped the planet's surface, creating oceans, mountains, and basins that define the geography we know today. Fossil evidence from the Neotethys provides additional insights into its history. Marine sediments contain the remains of ammonites, bivalves, corals, and other organisms that flourished in the warm waters of the ocean. These fossils allow paleontologists to reconstruct the changing environments, sea levels, and climatic conditions of the Mesozoic. Some regions of the Neotethys were rich in reefs and shallow seas, while others were deep, dark basins with limited light and low oxygen. By studying these fossils, scientists can trace migration patterns, evolutionary events, and even extinction episodes, all of which were influenced by the ocean's dynamic changes and its interactions with shifting continents. The Neotethys Ocean also played a role in connecting distant regions of the Mesozoic world. Ocean currents, influenced by the eastward orientation of the Neotethys, facilitated the movement of nutrients, heat, and marine organisms across vast distances. This connectivity allowed for the dispersal of species and the mixing of faunal communities, promoting evolutionary innovation and diversity. In addition, the ocean acted as a barrier at times, preventing the spread of some species and creating isolated ecosystems that evolved independently. These complex interactions between connectivity and isolation helped shape the patterns of biodiversity that we can trace through the fossil record today. In summary, the Neotethys Ocean was a defining feature of the Mesozoic world, stretching from roughly 250 million to 66 million years ago. Positioned between Laurasia to the north and Gondwana to the south, it was formed by the northward drift of Gondwana-derived microblocks like Samaria and grew into an expansive marine corridor. Its existence profoundly influenced the Earth's geography, climate, marine ecosystems, and even the formation of natural resources. The collision of its margins with Eurasia produced some of the world's most famous mountain ranges, including the Alps, Zagros, and Himalayas, while its gradual closure shaped the early forms of the Indian Ocean and the Mediterranean Sea. Through its complex and dynamic history, the Neotethys Ocean illustrates the power of tectonic forces, the interconnection of continents and oceans, and the intricate dance of land, sea, and life that has unfolded over hundreds of millions of years. Its legacy continues to be felt today, not only in the physical geography of the planet, but also in the patterns of biodiversity, climate, and natural resources that shape human civilization and the natural world alike. The Neotethys Ocean, therefore, stands as a remarkable chapter in Earth's history, a testament to the slow but unstoppable processes that have continuously reshaped our planet. By studying this ocean, scientists gain a deeper understanding of how ancient oceans influenced continental configurations, mountain building, climate, and life itself, providing a window into a world that existed hundreds of millions of years before humans appeared, yet whose effects are still deeply embedded in the modern Earth's landscapes and seas. Its story is one of movement, transformation, and enduring impact, offering a profound reminder of the dynamic and ever-changing nature of our planet. This account of the Neotethys Ocean draws on extensive research, including the geological and paleontological studies conducted by institutions like Harvard University, which have provided invaluable data on the processes of ocean formation, plate tectonics, and continental collision. By combining evidence from rocks, fossils, and structural geology, scientists have been able to reconstruct the vast history of the Neotethys and its role in shaping the Earth we know today. In reflecting on the Neotethys, it is clear that oceans are not merely passive bodies of water. They are dynamic entities that shape and are shaped by the movements of continents, the evolution of life, and the forces of the Earth itself. The Neotethys Ocean, in its millions of years of existence, exemplifies this intricate interplay and serves as a powerful example of the extraordinary history recorded in our planet's oceans and mountains. The Neotethys Ocean, therefore, is not only a subject of academic interest, but a key to understanding the ancient processes that have led to the present configuration of continents, seas, and ecosystems. Its history provides crucial insights into the evolution of the planet, demonstrating how the movements of land and sea have been intertwined with the development of mountains, biodiversity, and the distribution of natural resources that humans rely on today. By studying the Neotethys, we also gain perspective on the interconnectedness of geological, climatic, and biological systems. This ocean exemplifies how the physical movements of the Earth can drive profound changes in the environment and in the course of life itself, offering a vivid illustration of the complexity and beauty of Earth's geological history. The Neotethys Ocean's journey from an open seaway to a closed oceanic corridor illustrates the extraordinary power of tectonic processes over geological time. Its sediments, fossil records, and the mountains it helped create are all testimony to the scale and intensity of these processes. By examining these remnants, geologists, paleontologists, and climatologists can reconstruct the history of our planet, understand the forces that continue to shape it, and predict future changes in Earth's surface and climate. The Ural Ocean, also known as the Rheic Ocean, was a relatively small but important ancient body of water that once lay between two large landmasses called Siberia and Baltica. Although it does not receive as much attention as some of the larger prehistoric oceans, its existence played a crucial role in shaping the geography of the Earth, especially in the region that is now known for the Ural Mountains. These mountains today form a natural boundary between Europe and Asia, and they are a direct result of the processes that began with the opening and eventual closing of this ancient ocean. The formation of the Ural Ocean began during a time known as the Late Ordovician period, which was a distant era in Earth's past when life in the oceans was becoming more diverse and complex. During this time, the surface of the Earth was very different from what we see today. Instead of the continents being arranged in their current positions, they existed as separate landmasses scattered across the globe, slowly moving due to forces deep within the planet. These movements are driven by a process known as plate tectonics, where the Earth's outer shell is divided into large plates that float and shift over the semi-fluid layer beneath them. Before the Ural Ocean came into existence, there was an earlier ocean in the same region called the Kanti Ocean. This older ocean occupied the space between Siberia and Baltica before the events that led to the formation of the Ural Ocean began. Over time, a series of large islands, which had broken away from Siberia, began moving toward Baltica. These islands were not small in the way we think of islands today. They were large pieces of land, sometimes referred to as island arcs, and they carried with them volcanic activity and rising land. As these islands drifted closer to Baltica, they eventually collided with it. This process is known as a continental collision, and it is one of the most powerful forces in shaping the Earth's surface. When the islands struck Baltica, they caused the Kanti Ocean to begin closing. The ocean floor was pushed down and consumed beneath the colliding land masses in a process called subduction, while parts of the crust were squeezed, folded, and lifted. After the Kanti Ocean closed, the Ural Ocean formed in its place. It occupied a narrower space between Siberia and Baltica, acting as a kind of temporary waterway that separated these two large land masses. At this time, Baltica itself was part of a larger combined landmass known as Euramerica, which had formed from the earlier joining of other continents. This meant that the Ural Ocean was not just between two isolated pieces of land, but between major continental structures that were gradually coming together. As time passed and the Earth moved into the Devonian period, the Ural Ocean began to shrink. This shrinking did not happen suddenly, but was the result of the slow, steady movement of continents. Siberia, which lay to the east, began moving toward Baltica, while another landmass known as Kazakhstania also drifted closer. These movements reduced the width of the ocean over millions of years. During this time, the ocean likely changed in character. As it became narrower, it would have begun to resemble more of a seaway than a wide ocean. A seaway is a long, narrow body of water that connects larger bodies of water or separates land masses over a shorter distance. This transformation reflects the gradual closing of the gap between the continents. By the later part of the Devonian period and into the Carboniferous period, specifically during a stage known as the Mississippian, the Ural Ocean had shrunk significantly. It was no longer a broad ocean, but a more restricted marine passage. The continents continued to move closer together, driven by the constant forces of plate tectonics beneath the Earth's surface. Eventually, the movements of Siberia, Baltica, and Kazakhstania brought them into direct contact. This final collision occurred later in the Carboniferous period and marked the complete closure of the Ural Ocean. When an ocean closes in this way, the result is often the formation of a mountain range. This is exactly what happened here, leading to the creation of the Ural Mountains. The formation of the Ural Mountains is a classic example of what geologists call an orogeny, which is a mountain-building event caused by the collision of land masses. As the continents pressed against each other, layers of rock were compressed, folded, and pushed upward. Over time, this created a long chain of mountains stretching from north to south. These mountains have remained relatively stable over hundreds of millions of years, making them one of the older mountain ranges still visible on Earth today. The closure of the Ural Ocean and the formation of the Ural Mountains were not isolated events. They were part of a much larger process that was happening across the globe at the time. This process involved the coming together of nearly all the major landmasses to form a single supercontinent known as Pangaea. The joining of Siberia with Euramerica was one of the final steps in this massive assembly. Pangaea was a vast supercontinent that included almost all of Earth's land. Its formation had major effects on climate, ocean currents, and the distribution of life. With so much land connected, the interior regions of Pangaea became dry and extreme, while coastal areas experienced different environmental conditions. The closing of oceans like the Ural Ocean played a direct role in making this possible by removing the barriers that once separated continents. The history of the Ural Ocean also helps scientists understand how continents grow and change over time. The collisions that closed the ocean added pieces of land together, increasing the size of continents. Materials from the ocean floor, such as sediments and volcanic rocks, were scraped off and added to the edges of continents in a process known as accretion. This process contributed to the complex structure of the regions around the Ural Mountains. In addition to shaping the land, the closure of the Ural Ocean likely affected life in the region. Marine organisms that once lived in the ocean had to adapt as their environment changed. As the ocean became shallower and narrower, habitats would have shifted, and some species may have disappeared while others evolved. On land, the formation of mountains created new environments, influencing weather patterns and ecosystems. The rocks found in the Ural Mountains today provide evidence of this long history. Geologists study these rocks to learn about the ancient ocean and the events that led to its closure. They can identify different layers that were once part of the ocean floor, volcanic islands, and continental crust. These layers tell a story of movement, collision, and transformation that took place over millions of years. The Ural Ocean may have been small compared to other ancient oceans, but its impact was significant. It served as a temporary boundary between major land masses, and its closure helped bring those land masses together. The result was not only the formation of a major mountain range, but also a contribution to the creation of one of the most important geological features in Earth's history, the supercontinent Pangaea. The Kanti Ocean, also known as the Panthalassic Ocean, was a small and now completely vanished ocean that once existed in a distant and almost unimaginable past. It lay between the ancient continent of Baltica and a chain of volcanic islands known as the Kipchak Arc, close to what we now call Siberia. Even though it was not one of the largest oceans in Earth's history, its story is closely tied to some of the most important events that shaped the surface of our planet. The name of this ocean comes from two indigenous peoples who live in western Siberia today, the Kanti people and the Mansi people. These groups have lived for thousands of years in the region where the remains of this ancient ocean are now buried deep beneath the ground. By naming the ocean after them, scientists created a connection between the deep geological past and the human cultures that exist in that same region today. To understand how the Kanti Ocean came into existence, it is important to picture the Earth at the end of the Precambrian. At that time, the planet looked completely different. There were no familiar continents, and life itself was still very simple. Instead of many separate landmasses, there was a giant supercontinent called Pangaea. This enormous landmass gathered together most of Earth's land in one place, surrounded by vast oceans. However, the stability of this supercontinent did not last forever. Deep beneath the surface, powerful forces were at work. Heat from inside the Earth caused the crust to stretch and crack. Over time, these cracks grew wider, and the supercontinent began to break apart. This process is known as rifting, and it marked the beginning of a major transformation in Earth's geography. As Pangaea broke apart, it gave rise to a new arrangement of continents. One of the key landmasses formed during this time was Proto-Laurasia. This landmass did not remain whole for long. It too split apart into three separate continents: Laurentia, Baltica, and Siberia. Between these newly formed continents, oceans began to open. These oceans were not created all at once, but formed gradually as the land drifted apart. One of these bodies of water was the Kanti Ocean, which developed between Baltica and the island arc near Siberia. At roughly the same time, another important ocean, the Iapetus Ocean, opened up between Laurentia and Baltica. This shows how closely connected the formation of different oceans was during this period. The Kanti Ocean was not isolated. It was surrounded by several larger and more powerful oceans that influenced its development. To the north lay the vast Panthalassa, an enormous ocean that covered much of the planet. To the northeast was the Prototethys Ocean, and to the south and east stretched the Paleotethys Ocean. These surrounding oceans were much larger and played major roles in shaping global climate, ocean currents, and the movement of continents. The Kanti Ocean itself was relatively small, but that did not make it unimportant. Its position between Baltica and the island arc made it a place of active geological change. The Kipchak Arc, which formed one of its boundaries, was not a stable piece of land. Instead, it was a chain of volcanic islands created by tectonic activity. Beneath the ocean, one tectonic plate was being pushed under another in a process called subduction. This process caused magma to rise to the surface, forming volcanoes that eventually built up into islands. These island arcs were often unstable and constantly changing. Volcanoes erupted, islands grew, and sometimes parts of the arc sank back beneath the ocean. This made the region around the Kanti Ocean highly dynamic, with frequent geological activity shaping the landscape. As time passed, the continents continued to move. Baltica slowly drifted toward the island arc. This movement was incredibly slow, taking millions upon millions of years, but it was unstoppable. Eventually, the distance between Baltica and the island arc became smaller and smaller. The Kanti Ocean, which once lay between them, began to shrink. The closing of the Kanti Ocean was caused by a major collision between Baltica and an island arc known as the Sakmarian Arc. As these two landmasses moved toward each other, the ocean floor between them was gradually destroyed. The process that created the ocean was now working in reverse. Instead of new crust forming and pushing the continents apart, the oceanic crust was being pulled down into the earth and recycled. This collision was not gentle. When Baltica and the island arc finally met, the impact caused massive changes. The ocean between them disappeared, and the land was pushed upward, forming new geological structures. Mountains may have formed as a result of this collision, although much of the evidence has been altered or buried over time. At the northeastern end of the island arc, something new appeared as a result of these changes. A new body of water known as the Ural Ocean began to develop. This shows how the Earth's surface is always changing. As one ocean closes, another can open somewhere else, continuing the endless cycle of creation and destruction. The time period during which the Kanti Ocean existed stretched from near the end of the Precambrian into the Silurian period. This was a time of major transformation on Earth. Life in the oceans was becoming more complex, with early marine organisms evolving and spreading. Although the Kanti Ocean itself has left behind few direct traces of life, it was part of this larger world where life was beginning to flourish. The geological processes that shape the Kanti Ocean are part of a larger system known as plate tectonics. This system explains how the Earth's outer shell is divided into large pieces called plates, which move slowly over time. These movements create oceans, mountains, earthquakes, and volcanoes. The story of the Kanti Ocean is one small piece of this much larger puzzle. Even though the Kanti Ocean no longer exists, its history is still recorded in the rocks beneath our feet. Geologists study these rocks to understand how the ocean formed, evolved, and disappeared. By examining the structure of the Earth's crust, the types of rocks present, and the patterns of ancient tectonic activity, they can reconstruct the story of this long-lost ocean. The region where the Kanti Ocean once existed is now part of the landmass of Eurasia. Over hundreds of millions of years, additional collisions and changes have reshaped the area many times. The evidence of the ocean has been altered, buried, and sometimes destroyed, making it difficult to piece together its full history. Yet, through careful study, scientists have been able to uncover enough clues to tell its story. The Kanti Ocean may have been small compared to giants like Panthalassa, but it played its role in the grand history of the Earth. Its formation marked a time when continents were breaking apart and new oceans were being born. Its existence reflected a period of active geological change, with volcanic arcs and shifting plates shaping the planet's surface. Its closure marked another important step, as continents came together and new geological features were formed. This cycle of opening and closing oceans is one of the defining features of Earth's history. Oceans do not last forever. They are born when continents split apart, and they disappear when those continents come back together. The Kanti Ocean is a perfect example of this process, showing both the beginning and the end of an ocean's life. The Morovia Ocean was an enormous, almost planet-wide body of water that is believed to have existed during a very ancient chapter of Earth's history known as the Neoproterozoic era. This era stretched from about 1 billion years ago to roughly 541 million years ago, a span of time so vast that it is difficult to truly imagine. During this period, the Earth looked very different from what we see today. Instead of many separate continents scattered across the globe, most of the land was joined together into a single giant supercontinent called Rodinia. Surrounding this immense landmass was a single global ocean, and that ocean is what scientists refer to as the Morovia Ocean. The idea of a global ocean may seem unusual at first, but when we look back into deep time, it becomes clear that Earth has gone through many different arrangements of land and sea. Today, we have several large oceans, including the Atlantic, Pacific, and Indian Oceans, each separated by continents. But in the distant past, the Earth's crust behaved like a slowly shifting puzzle, with pieces moving, colliding, and breaking apart over millions upon millions of years. During the time of Rodinia, these pieces had come together to form one massive block of land, leaving one continuous ocean to cover the rest of the planet. The Morovia Ocean was not just large, it was truly immense, possibly covering most of the Earth's surface. Imagine standing on the edge of Rodinia and looking out across an endless expanse of water, stretching farther than the eye could ever see. There would be no familiar coastlines across the horizon, no nearby islands, and no ships crossing the waters. it would be a world dominated by ocean, where the land formed only a single gigantic island in a vast watery sphere. The formation of Rodinia itself was the result of powerful forces deep within the Earth. The planet's outer layer, known as the crust, is divided into large plates that slowly move over time. These movements are driven by heat rising from the Earth's interior, causing the plates to drift, collide, and sometimes pull apart. Over hundreds of millions of years, smaller landmasses gradually came together, merging into the supercontinent Rodinia. As this happened, the oceans that once existed between these landmasses were closed, and their waters became part of the larger global ocean that surrounded the supercontinent. The Morovia Ocean likely played a major role in shaping the climate and environment of the Earth during the Neo-Proterozoic era. Oceans are not just bodies of water. They are powerful systems that store heat, move currents, and influence weather patterns. A global ocean of this size would have had a profound effect on how heat was distributed around the planet. Warm water near the equator would have moved toward the poles, while cooler water would have circulated back toward the equator. This constant movement would have helped regulate the Earth's temperature, although not always in ways that were stable or predictable. One of the most dramatic events that may have taken place during the time of the Morovia Ocean is known as Snowball Earth. This idea suggests that at certain points during the Neo-Proterozoic era, the Earth became almost entirely covered in ice. Glaciers may have extended from the poles all the way to the equator, and the oceans themselves could have frozen over. If this happened, then the Morovia Ocean would not have been a liquid expanse of water, but rather a frozen shell covering much of the planet. Scientists believe that during these extreme periods, the ice covering the ocean may have been incredibly thick, possibly reaching depths of about 2 kilometers. That is roughly the height of some of the tallest mountains on Earth today. Underneath this thick layer of ice, however, the ocean would not have been completely frozen. The heat from the Earth's interior, along with pressure from the overlying ice, would have kept some of the water in a liquid state beneath the surface. The idea of a frozen ocean may seem like it would make life impossible, but evidence suggests that life managed to survive even during these harsh conditions. Simple forms of life, such as microscopic organisms, likely lived in the ocean beneath the ice. They may have relied on chemical energy from hydrothermal vents on the ocean floor, where hot, mineral-rich water flowed out from the Earth's interior. These environments could have provided the warmth and nutrients needed for life to continue, even when the surface of the planet was locked in ice. The existence of the Morovia Ocean also helps scientists understand how the Earth's continents have changed over time. After millions of years, the supercontinent Rodinia began to break apart. The same forces that had once brought the land masses together started to pull them apart again. Cracks formed in the crust, and molten rock rose up from below, creating new ocean basins. As Rodinia split, new oceans began to form, and the single global ocean of Morovia was gradually divided into smaller bodies of water. This process of breaking apart and coming back together is known as the supercontinent cycle. Over billions of years, Earth's continents have repeatedly merged into supercontinents and then split apart again. Rodinia was just one of several supercontinents in this cycle, and the Morovia Ocean was one of the great oceans that existed during these times of unity. Later supercontinents, such as Pangaea, would also be surrounded by large oceans, although none may have been as truly global as Morovia is thought to have been. Studying the Morovia Ocean is not easy, because there are no direct remains of it that we can see today. Unlike modern oceans, which we can explore with ships and submarines, ancient oceans leave behind only indirect evidence. Scientists must rely on clues found in rocks, minerals, and fossils to piece together what these ancient environments were like. For example, certain types of rocks form only in ocean settings, and by studying their composition and location, scientists can learn about the conditions that existed when they were formed. One important clue comes from sedimentary rocks, which are formed from layers of material that settle at the bottom of oceans and seas. These layers can contain tiny fossils, chemical traces, and other evidence that reveal information about the ancient ocean. By studying these rocks, scientists can estimate things like the temperature of the water, the presence of ice, and the types of life that existed at the time. Another important source of information comes from the study of isotopes, which are different forms of the same chemical element. The ratios of certain isotopes in rocks can tell scientists about past climates and ocean conditions. For example, changes in the ratio of oxygen isotopes can indicate whether the Earth was experiencing warmer or colder conditions. These kinds of studies have provided support for the idea that the Earth experienced extreme glaciations during the time of the Morovia Ocean. The concept of the Morovia Ocean also raises interesting questions about how life evolved on Earth. During the Neo-Proterozoic era, life was still relatively simple, consisting mostly of single-celled organisms and early multicellular forms. However, by the end of this era, more complex life forms began to appear, setting the stage for the explosion of life that would occur in the following period, known as the Cambrian. Some scientists believe that the extreme conditions associated with events like Snowball Earth may have played a role in driving evolution. When the environment becomes harsh, only the most adaptable organisms survive. These survivors may then evolve new traits that allow them to take advantage of changing conditions. In this way, the challenges posed by a frozen world may have helped push life toward greater complexity. The Prototethys Ocean was one of the great early oceans of the Earth, forming during a time when the surface of the planet looked completely different from today. It existed from the closing part of the Ediacaran period and continued through much of the Paleozoic era, lasting from about 550 million years ago until roughly 330 million years ago. During this immense stretch of time, the Earth was undergoing constant change, with continents slowly drifting, oceans opening and closing, and life gradually becoming more complex. The name Prototethys is used by geologists to describe what they believe was an early ocean that came before another later and better-known ocean called the Paleotethys Ocean. However, the idea of the Prototethys is not always agreed upon. Some scientists use the name in slightly different ways, and others are not fully convinced that such an ocean existed exactly as described. This makes the Prototethys not just an ancient ocean, but also a subject of scientific debate and investigation, showing how our understanding of Earth's past is still growing and changing. To understand how this ocean formed, it is important to look at an even earlier stage in Earth's history, when most of the land on the planet was joined together in a supercontinent known as Pannotia. This supercontinent existed before the more famous Gondwana and was made up of many of the land masses that would later separate and move across the globe. Over time, powerful forces inside the Earth caused Pannotia to break apart. This process is known as rifting, where the crust stretches and splits, allowing molten rock to rise from below and create new ocean floor. As Pannotia began to break up, one part of it started to form what would later become the massive southern supercontinent known as Gondwana. At the same time, other pieces of land drifted away and came together to form a northern grouping sometimes called Proto-Laurasia. This included early versions of continents such as Laurentia, Baltica, and Siberia. As these landmasses separated from Gondwana, a new ocean basin opened up between them. This growing body of water is what geologists refer to as the Prototethys Ocean. At the same time, the Earth was also home to an enormous global ocean known as Panthalassa, which covered most of the planet. The Prototethys was not alone. It existed as part of a complex system of oceans and seas. To the north of Prototethys lay Panthallassa, but the two were not directly connected in a simple way. Instead, they were separated in places by chains of volcanic islands known as island arcs, as well as smaller continental fragments such as Kazakhstania. These features were created by tectonic activity, especially where one plate was forced beneath another in a process called subduction. During the early part of its existence, particularly in the Cambrian period, the Prototethys Ocean continued to grow wider. This was a time when life in the oceans was beginning to flourish in new and exciting ways. The Cambrian is famous for what scientists call the Cambrian explosion, a period when many new forms of life appeared in the seas. Although the Prototethys itself is known mainly through rocks and geological evidence, it would have been home to many of these early marine creatures. As time passed into the Ordovician period, the Prototethys reached one of its largest sizes. During this time, it stretched widely between different continental blocks. To one side lay parts of Gondwana, while on the other side were continents like Siberia and Baltica. The ocean floor was constantly changing as new crust formed in some areas and was destroyed in others through subduction. One important idea proposed by geologists such as Daniel Bernoulli von Raumer and Gerard Stamfli is that the Prototethys was part of a much larger oceanic system. In their view, it formed the eastern part of a wide ocean domain, while oceans like the Iapetus Ocean and the Tornquist Ocean made up the western parts. According to this idea, the entire system was slowly being pushed beneath the northern edge of Gondwana through subduction. This means that while the ocean was expanding in some areas, it was also being consumed in others, showing the dynamic and ever-changing nature of Earth's surface. During the early part of the Ordovician, roughly between 500 million and 480 million years ago, parts of the Prototethys began to be pushed under a region known as Cadomia. This was likely connected to a geological feature called a back arc basin, specifically the Chamrus back arc basin. Back arc basins form behind volcanic arcs, where the crust is being pulled apart, even as subduction continues nearby. This complex interaction of forces shows just how active the region around Prototethys was during this time. Another group of scientists, including Trond Torsvik and Christopher Robert Scotese Cox, have used a different name for a similar ocean. They called it the Rheic Ocean, describing a body of water that existed during the Cambrian and Ordovician periods and separated Baltica from Gondwana. This difference in naming highlights the challenges scientists face when trying to reconstruct events that happened hundreds of millions of years ago. The rocks that remain are often incomplete or have been altered by later processes, making it difficult to piece together a clear picture. Not all geologists agree that the Prototethys Ocean existed as a separate and clearly defined ocean. Some argue that the evidence is not strong enough, or that what is being described as Prototethys may actually have been part of a larger or different ocean system. This disagreement is an important part of science, showing that ideas are constantly tested, questioned, and improved over time. As the Earth moved into the Silurian period, the Prototethys began to change in a new way. Instead of continuing to grow, it started to shrink. This happened because of the movement of several continental blocks. The North China and South China blocks, which had once been part of or close to Gondwana, began to drift northward. As they moved, they reduced the size of the ocean between them and other land masses. Later, during the Devonian period, another important event took place. A smaller continental fragment known as Kazakhstania moved and eventually collided with Siberia. This collision further reduced the size of the Prototethys Ocean. Each collision between land masses closed off parts of the ocean, pushing water aside and raising mountains where the continents met. Finally, during the Carboniferous period, the Prototethys Ocean came to an end. This happened when the North China Craton collided with the combined landmass of Siberia and Kazakhstania. This final collision closed the remaining parts of the ocean, turning what had once been a vast body of water into land. While the Prototethys was disappearing, another ocean was beginning to take its place. The Paleotethys Ocean started to expand, becoming the next major ocean in that region. This pattern of one ocean closing while another opens is a common theme in Earth's history, driven by the slow but powerful movements of tectonic plates. The Iapetus Ocean was one of the ancient oceans that existed hundreds of millions of years ago, during a time when the Earth looked very different from how it does today. This ocean first appeared in the late Neoproterozoic era and continued to exist into the early Paleozoic era, roughly between 600 million years ago and 400 million years ago. It occupied a position in the southern hemisphere, lying between vast landmasses that geologists today refer to as Laurentia, Baltica, and Avalonia. These continents were separate from each other, forming islands and stretches of continental crust scattered across the ancient oceans, and the Iapetus Ocean filled the space between them like a watery highway that connected and separated these landmasses at the same time. Over time, the Iapetus Ocean ceased to exist as a distinct body of water because the continents surrounding it began to drift toward each other. This drift was driven by the movement of the Earth's tectonic plates, large sections of the Earth's crust that slowly shift over geological time. As Laurentia, Baltica, and Avalonia approached each other, the ocean that once lay between them gradually narrowed and eventually disappeared. Its closure occurred through a series of dramatic geological events known as orogenies, or mountain-building episodes. Specifically, the Tectonic, Caledonian, and Akkadian orogenies played critical roles in this process. These events involved the collision and welding together of the continents, ultimately forming a single large landmass known to geologists as Euramerica. The southern portion of the Iapetus Ocean is thought to have closed in a similar but slightly more distant scenario. Here, the closure occurred when the western edge of the massive Gondwana continent, located in the southern hemisphere and including much of what is today South America, collided with Laurentia. This collision is reflected in geological formations seen today in both North and South America, suggesting that the tectonic orogeny of the north was a continuation of a chain of mountain-building activity visible in Argentina, called the Famitinian orogeny. Together, these events stitched together previously separate continents into larger, more continuous landmasses. Interestingly, the Iapetus Ocean can be seen as a sort of ancient precursor to the modern Atlantic Ocean. Much like the Atlantic, the Iapetus opened along zones where the Earth's crust was pulling apart, and its expansion and later closure show parallels with the processes that later created the Atlantic Ocean during the Jurassic period, nearly 150 million years ago. In recognition of this connection, the ocean was named after Iapetus, a titan in Greek mythology who was the father of Atlas, the figure whose name would later be given to the Atlantic Ocean. This naming reflects both a symbolic and scientific link between the two oceans, highlighting how Earth's history repeats in cycles over immense spans of time. The story of the Iapetus Ocean began to emerge more clearly in the early 20th century, when American paleontologist Charles Walcott made important observations. Walcott studied trilobites, a type of extinct marine arthropod that thrived in shallow seas, which lived on the continental shelves of Laurentia and Baltica. He noticed significant differences in these trilobite communities. For example, Laurentia was home to a group called the Olanellidae, sometimes referred to as the Pacific fauna, and their fossils were found in areas that are now part of western Newfoundland and Scotland. In contrast, Baltica contained a distinct group called the Paradoxididae, known as the Atlantic fauna, which appeared in the southern regions of the British Isles and eastern Newfoundland. These differences suggested that the two continental regions had been separated by a significant marine barrier during the early Paleozoic, a separation that Walcott and his contemporaries described as a geosyncline, or a large trough-like depression in the Earth's crust. This geosyncline, they believed, had kept the faunas of Scotland and England apart, creating distinct marine environments. Later developments in geology, particularly the establishment of plate tectonic theory in the 1960s, transformed our understanding of these ancient oceans. Geologists such as Arthur Holmes and John Tuzo Wilson recognized that the Atlantic Ocean could not have formed in isolation. It must have had a predecessor, and the Iapetus Ocean fit this role. Wilson, in particular, noted that the Atlantic had opened along roughly the same zone where the Iapetus had once closed, leading him to formulate the Wilson cycle. This cycle describes the repeated opening and closing of oceans over hundreds of millions of years, as continents drift apart and then collide again, producing mountain ranges and new ocean basins in the process. The Iapetus Ocean, therefore, represents a fundamental example of the cyclical nature of Earth's tectonic activity. Geological evidence of the Iapetus Ocean's formation is found in several parts of the world. In Scandinavia, for instance, basaltic dikes have been dated to between 670 million and 650 million years ago. These dikes are fractures in the Earth's crust through which molten rock once flowed, and they indicate that rifting, or the pulling apart of the continental crust, had begun by that time. This rifting would eventually create the basin that became the Iapetus Ocean. Similarly, in Newfoundland and Labrador, geologists have studied the long-range dikes, which formed during the same rifting events, providing further evidence that the Iapetus Ocean was taking shape. Additional geological formations, such as the Fen complex in Norway and the Alno complex in Sweden, are interpreted as the result of mild extension in the ancient continent of Baltica that accompanied the opening of the Iapetus Ocean. The timing of the ocean's formation, however, varied across different regions. The eastern Iapetus Ocean, located between Laurentia and Baltica, is thought to have begun opening around 590 million years ago, coinciding with the emplacement of the central Iapetus magmatic province. This was a large volcanic and magmatic event that marked the initial separation of the two continents. Meanwhile, the southern portion of the ocean, situated between Laurentia and southwestern Gondwana, began to open approximately 550 million years ago, near the end of the Ediacaran period. This period immediately preceded the Cambrian, a time known for the explosive diversification of life. At the same time that the southern Iapetus was opening, another ocean farther east, called the Adamastor Ocean, was closing. These overlapping events illustrate the dynamic and complex nature of Earth's oceans during this period. It is worth noting that the opening of the Iapetus Ocean appears to post-date the opening of another ancient ocean, the Puncoviscana Ocean, which likely formed around 700 million years ago, as Laurentia began drifting away from Amazonia. The Iapetus Ocean and the Puncoviscana Ocean were separated by a long, narrow strip of continental crust known as the Arequipa Antofalla terrane, yet their formation seems to have occurred independently. This shows that multiple oceanic basins could form simultaneously in different parts of the globe, each influenced by local tectonic conditions rather than being directly connected. Along the western edge of the Iapetus Ocean, the early Cambrian, beginning about 540 million years ago, witnessed the development of a volcanic island arc. This arc emerged above a subduction zone, a region where one section of the oceanic crust slid beneath another. As the oceanic lithosphere of the Iapetus Ocean subducted southward, magma was generated and rose to form islands, creating a chain of volcanoes that marked the leading edge of tectonic convergence. This process also caused the western portion of the Iapetus Ocean to gradually shrink as oceanic crust was consumed by subduction. Farther north and east, similar processes took place. Avalonia and Baltica began moving toward Laurentia during the Ordovician period, roughly 488 to 444 million years ago. These convergences further narrowed the ocean and set the stage for its eventual closure. Evidence from the fossil record confirms these changes. Trilobites living on the continental shelves of Baltica and Laurentia remained distinct during the Ordovician, reflecting the continued separation of the continents by oceanic waters. However, as the continents drew closer, especially during the Silurian period, approximately 444 to 420 million years ago, trilobite faunas began to mix. This progressive blending of species reflects the gradual closing of the ocean and the establishment of new ecological connections between previously isolated marine habitats. The closure of the Iapetus Ocean occurred in stages. In the west, the Tectonic orogeny, which took place between 480 and 430 million years ago, marked a significant collision event. During this orogeny, the volcanic island arc formed above the subduction zone collided with Laurentia, effectively consuming the western branch of the ocean. Some geologists also consider the oceanic basin south of the island arc to be part of the Iapetus, which closed later during the Akkadian orogeny when Avalonia collided with Laurentia. Meanwhile, the southern Iapetus Ocean, as previously mentioned, closed when Laurentia collided with western Gondwana. This collision produced mountain ranges and deformed rocks that remain visible today in regions such as Argentina and parts of North America, providing a record of the immense forces involved. In the eastern regions, the closure occurred as well. The Tornquist Sea, a branch of the Iapetus, disappeared during the late Ordovician when Avalonia and Baltica collided. The main branch of the ocean, separating Baltica, Avalonia, and Laurentia, closed during the Grampian and Scandian phases of the Caledonian orogeny, which occurred between 440 and 420 million years ago. By this time, tectonic forces had finally brought the continents together, leaving no significant open ocean between them. By the end of the Silurian period, approximately 420 million years ago, the Iapetus Ocean had completely vanished. Its disappearance marked the creation of a new continental landmass composed of the once separate continents of Laurentia, Baltica, and Avalonia. This newly assembled continent, called Laurasia, would later form the northern part of the supercontinent Pangaea, a vast landmass that encompassed nearly all of the Earth's continents during the late Paleozoic and early Mesozoic eras. The history of the Iapetus Ocean, therefore, represents a critical chapter in the story of continental assembly, ocean formation, and the tectonic cycles that have shaped the surface of the Earth over hundreds of millions of years. The geological processes that created, expanded, and eventually closed the Iapetus Ocean are a vivid illustration of the Earth's dynamic nature. Rifting, subduction, island arc formation, and continental collision all played essential roles in the life cycle of this ancient ocean. Its formation was marked by the stretching and thinning of continental crust, volcanic activity, and the creation of new oceanic lithosphere. Its closure was characterized by the consumption of oceanic crust at subduction zones, the collision of volcanic arcs with continents, and the ultimate welding together of separate land masses into a single continental mass. Fossil evidence, particularly from trilobites, provides a unique window into these ancient processes. The distinct species found on Laurentia, Baltica, and Avalonia tell a story of isolation and gradual reconnection. As the continents drifted and collided, these marine organisms recorded the changing geography, giving modern scientists a biological measure of tectonic movements. Trilobite faunas from the Ordovician and Silurian periods, for instance, reveal the gradual merging of previously isolated ecosystems, reflecting the progressive narrowing of the Iapetus Ocean. Geologists also rely on the study of rock formations to reconstruct the ocean's history. Basaltic dikes, volcanic complexes, and magmatic provinces mark the sites of rifting and ocean opening, while orogenic belts and deformed rock sequences reveal the sites of collisions and ocean closure. The central Iapetus magmatic province, the Fen complex, the Alno complex, and the long-range dikes are all examples of geological features that serve as evidence for the ocean's opening and evolution. Similarly, the Tectonic, Akkadian, and Caledonian orogenies leave behind mountain ranges, metamorphic rocks, and fault systems that record the dramatic collisions that closed the ocean and created new continental crust. The Iapetus Ocean story is also closely tied to the concept of supercontinents and oceanic cycles. The opening and closing of this ocean demonstrate how the Earth's surface undergoes continuous transformation, with oceans forming and disappearing as continents drift across the globe. The Iapetus Ocean opened as continents separated, expanded as rifting progressed, and eventually closed as tectonic forces drove continents together. Its existence provides a clear example of the Wilson cycle, the repeated pattern of ocean formation and closure that shapes the Earth's continents over geological time. Moreover, the Iapetus Ocean shows the interconnectedness of global tectonic events. Its opening coincided with the closure of other oceans, such as the Adamastor, while its formation post-dated earlier oceans like the Puncoviscana. This highlights the fact that Earth's tectonic history is not a linear sequence of events, but rather a complex, overlapping series of processes that interact across the planet. Each ocean, each continental drift, and each collision is part of a larger dynamic system, demonstrating the interconnectedness of geological phenomena over hundreds of millions of years. The Iapetus Ocean was a vast body of water that existed during a very distant chapter of Earth's history, stretching from the late Neoproterozoic into the early Paleozoic, roughly between 600 million and 400 million years ago. At that time, the continents were not arranged the way they are today. Instead, several ancient land masses, known as paleocontinents, were scattered across the globe. This ocean lay mainly in the southern hemisphere and formed a wide, watery barrier between three of these major land masses, Laurentia, Baltica, and Avalonia. Over an immense span of time, the Iapetus Ocean did not remain unchanged. It slowly shrank and eventually disappeared as the continents on either side of it moved closer together. These movements were not sudden or violent in a human sense, but incredibly slow, happening over tens of millions of years as Earth's crust shifted and rearranged itself. The closing of this ocean was marked by a series of powerful mountain-building events known as orogenies, including the Tectonic orogeny, the Caledonian orogeny, and the Akkadian orogeny. During these events, the once separated continents collided and fused together, forming a much larger landmass called Euramerica. There is also an idea that a southern part of the Iapetus Ocean closed in a similar way, through collisions involving the western edge of Gondwana and Laurentia. This process may have been linked to the Famattinian orogeny as well as the Tectonic orogeny, suggesting that different parts of the ocean were closing at different times, but through related tectonic processes. Because of where it was located, the Iapetus Ocean is often seen as an early version, or a kind of ancestor, of the Atlantic Ocean. Long after the Iapetus had vanished, the continents that once bordered it would drift apart again, eventually forming the coastlines of the modern Atlantic. In fact, the way the Iapetus Ocean first opened shows strong similarities to how the Atlantic Ocean began to form much later during the Jurassic period. Its name reflects this connection. It was named after Iapetus, a figure in Greek mythology who was said to be the father of Atlas, the namesake of the Atlantic Ocean. In the early years of the 20th century, scientists began to notice clues that hinted at the existence of this lost ocean. One important figure was Charles Walcott, who studied ancient marine fossils called trilobites. These small, hard-shelled creatures lived on the seafloor and left behind fossils that are still found today. Walcott observed that trilobites from Laurentia were very different from those found in Baltica. For example, species belonging to the Olenalidae, often called the Pacific fauna, were found in places like Scotland and western Newfoundland, while species from the Paradoxididae, known as the Atlantic fauna, appeared in the southern British Isles and eastern Newfoundland. These differences suggested that the regions had once been separated by a large ocean, preventing the mixing of species. At that time, geologists did not yet fully understand plate tectonics, so they proposed the idea of a deep trough, or geosyncline, lying between areas such as Scotland and England. This hypothetical feature was thought to explain why the fossils were so different on either side. Everything changed in the 1960s, when the theory of plate tectonics became widely accepted. Scientists like Arthur Holmes and John Tuzo Wilson realized that oceans can open and close over time as continents move. Wilson, in particular, noticed that the Atlantic Ocean seemed to have formed in roughly the same place where an older ocean had once existed. This insight led him to propose what is now called the Wilson cycle, a concept describing how oceans are born, grow, shrink, and eventually disappear. Physical evidence for the opening of the Iapetus Ocean can still be found today in ancient rocks. In parts of Scandinavia, for example, there are long, dark sheets of volcanic rock known as basaltic dikes that formed between about 670 million and 650 million years ago. These rocks are believed to have formed when the Earth's crust began to stretch and crack, a process known as rifting, which eventually led to the creation of the ocean basin. Similar features, such as the long-range dikes in Newfoundland and Labrador, also point to this period of early stretching and separation. Other geological formations, like the Fen complex in Norway and the Alnö complex in Sweden, may have formed as a result of mild tectonic stretching in the ancient continent of Baltica after the ocean began to open. These features act like fingerprints, preserving the story of how the land once pulled apart. The opening of the Iapetus Ocean did not happen all at once, but in stages. The eastern part likely began forming around 590 million years ago, when large amounts of molten rock rose up and created what is known as the Central Iapetus Magmatic Province between Laurentia and Baltica. The southern part opened slightly later, around 550 million years ago, as Laurentia drifted away from what is now South America, then part of Gondwana. Around the same time, another ocean to the east, called the Adamastor Ocean, was closing. Even earlier, another ocean known as the Punkoviskana Ocean may have opened around 700 million years ago, when Laurentia separated from the Amazonian region. The Iapetus Ocean was separated from this earlier ocean by a long, narrow strip of land called the Arequipa Antofalla terrane. Although these oceans formed at different times, scientists believe their origins were not directly connected. As time went on, the Iapetus Ocean began to shrink. To the southwest, a chain of volcanic islands started forming from the early Cambrian period, around 540 million years ago. This island arc developed above a subduction zone, where one part of the ocean floor was being forced beneath another. This process slowly consumed the oceanic crust, making the ocean narrower. From about 550 million years ago onward, the western part of the ocean continued to shrink as subduction progressed. Meanwhile, in the north and east, the continents of Avalonia and Baltica began moving steadily toward Laurentia, starting in the Ordovician period, which lasted from about 488 million to 444 million years ago. Fossils provide a fascinating record of these changes. During the Ordovician, trilobite species in Baltica and Laurentia were still quite different, showing that the ocean was still wide enough to keep them apart. However, by the Silurian period, these differences began to fade as species from both sides started to mix. This gradual blending of life forms reflected the closing distance between the continents. Eventually, the ocean disappeared entirely. In the west, it closed during the Tectonic orogeny between about 480 million and 430 million years ago, when a volcanic island arc collided with Laurentia. Some scientists believe that a southern branch of the ocean also closed later during the Akkadian orogeny, when Avalonia finally collided with Laurentia. At the same time, the eastern parts of the ocean were also closing. A smaller body of water known as the Tornquist Sea between Avalonia and Baltica vanished during the late Ordovician. The main eastern branch of the Iapetus Ocean closed later during different phases of the Caledonian orogeny, including the Grampian phase and the Scandian phase, between about 440 million and 420 million years ago. By the end of the Silurian period, around 420 million years ago, the Iapetus Ocean had completely vanished. In its place stood a newly formed continent called Laurasia, created from the merging of Laurentia, Baltica, and Avalonia. This landmass would later become the northern half of the supercontinent Pangaea, one of the most famous and important stages in Earth's geological history.